Looks like we're live. Hello everyone and welcome to yet another Azuzin session. Let's make a little bit of an announcement and officially start the stream as usual. So let's do the usual red circle live on Twitch. And what are we doing today on Twitch.television, a website? So today we continue doing machine learning in C, but specifically today we're going to be developing a new framework for neural networks in C. That's fucking right. It is possible in 2023. Let's go. So I'm gonna give the link to where we're doing all that, twitch.tv/sodding, and I'm gonna ping everyone who's interested in being pinged. And there we go. The stream has officially started. Holy fucking shit. That's how we're supposed to act in 2023 on social media. Otherwise, nobody's gonna watch you because you have to be engaging. I wanna fucking die. Anyway, hello everyone. So. Hello, welcome. So on the previous stream, we essentially explored a paradigm called machine learning, right? So in this paradigm, you create some sort of a mathematical model of some sort of a process, right? So, and essentially you do not create that model directly. Right, so the model has a bunch of parameters. You do not specify the parameters of the models directly. What you do, you write a description of the behavior of the model that you desire, so-called cost function, right? So it's basically like a distance between how the model actually behaves and how you want it to behave. And then you basically tweak and mess with parameters algorithmically, purely algorithmically, until the cost function becomes like small enough that you would say that's a good model, right? So that's a good model. So essentially this entire process takes your description of the model and just, you know, finds the model that fits the best that specific description. So it's kind of a different paradigm of programming, so to speak, right? So you're not creating a thing directly, you create a thing that describes how the thing has to behave, right? And of course, because of it's a different paradigm, it has its own strengths and weaknesses. Some things are easy in that paradigm, some things are difficult, and vice versa, right? So yeah, and on the previous stream, we actually started with very simple examples. We considered 3 different models. So you can find the notes from the previous stream in here. So I'm going to copy paste them in the chat. So here they are, right? And for people who's watching me on YouTube, it's going to be in the description. Right, so what we started with a very simple model. Maybe we can even take a look at that, right? So let's take a look at the ML notes. So the model is called Twice. Right, and essentially, what's up with that model, right? So you are supposed to supply a number x into that model, right? So, and the model itself, it has only one parameter, right? Which is like, you know, the weight of the connection if we look at that model as a single neuron. But if we look at it as a single neuron, we're supposed to actually put weight on the connection in here, right? Because that's the strength of connection, but let's not get too wind up about all of that. And on the in the output, you would see this thing being multiplied by 2. So here you have 2x. Right, and essentially, the simplest solution for that model is just to say w equal to 2, but we don't know that. We pretended that that's a very difficult, very complicated model, and we wanted to use machine learning approach to actually find that specific solution. Right, and we used a very simple approach where we define the cost function, right? And then we used very simple finite differences approach. Essentially, we wiggled the parameters of the model by a certain epsilon. And if that drives the cost function down, we just increased by that specific epsilon, that specific direction, nothing particularly special. So I think in this specific case, I also introduced the biases, right? So to demonstrate how it works, it's just addition number, but it doesn't really matter. So this was the Twice model, right? It just multiplies the specific thing by 2. Right, so this is a Twice. So the other thing we explored a model with yet a single neuron, right, but already with 2 connections, right? So there was 2 connections in here. So we have a value x1 and x2. There is 2 weights in here, w1 and w2, and also there is like one bias specifically for that neuron, And essentially what we did with that single neuron, we modeled a couple of, gates, right? And a couple of like binary gates, like OR gate, AND gate, and so on and so forth. And we also demonstrated that it is not really possible to model XOR gate with just a single neuron, right? So it's not particularly possible. And to model XOR gate, right? To model a XOR gate, we have to create a more complicated architecture of the neural network, right? So we had to create 3 separate neurons, right? 3 separate neurons. So the input goes into these 2, right? So actually, you have 2 inputs in here. So this is not like an actual neurons of the neural network, but they're sort of like an input. So this is X1 and this is X2. And the first input connects to here, right? And the second one connects to here. And again, these 2 also connect to these 2 things, right? So, and then the final result is combined by this neuron, right? The final result is combined by this neuron. So this particular thing has at least like 6 weights, because each of the connection has its own weight. So there's 4 connections in here and 2 connections in here. So there's 6 weights, and each of the neuron have their own bias, like B1, B2, and B3. So there was in total like 9 parameters in that model. So the way we actually represented that specific model, right? The way we represented that specific model is just like we literally listed all of these parameters in a structure, and we passed it around, and so on and so forth, right? So the problem with this entire stuff is that this particular approach is not scalable, right? Because we already have like 3 neurons in here, right? But it's already kind of difficult to work with. We had to do a lot of copy paste, right? Just to work with all of that. We could have actually put all of that into an array, like a linear array of those things, but that doesn't describe the architecture of the neural network. What if we have 3 neurons but organized in a completely different architecture, right? So here they're like sort of in a triangle, but what if we just straighten them up linearly? So how do we describe that? We literally have to change the code of the function that forwards information in here. So that the actual topology, so to speak, of the neural network is described by literally this code. Right, it's sort of like hard-coded. How can we make it more flexible? So yeah, and that's the problem that I wanted to tackle today. There is a very convenient and kind of like an elegant way of representing neural networks in the memory of a computer. And so we're gonna explore that sort of technique, and we're gonna build a framework around the technique today. So that's the plan for today. So we got some subs, right? So we got some subs that I would like to acknowledge, right? So let me quickly do that. So we have some people. Silence Showman, thank you so much for tier 1 subscription. They subscribed actually off screen, but I want to acknowledge them anyway. Jack Patterns, thank you so much for Twitch Prime. Swinging Saucer, thank you so much for Twitch Prime. Lindro Braga, thank you so much for Twitch Prime. Azura Akimori, thank you so much for Twitch Prime with the message 11 months. So cool. That's actually pretty cool. Almost a year, by the way. Almost a year. Not Ignacio, I hope I pronounced your name correctly. Thank you so much for Twitch Prime subscription with the message hello, a smiley face. Hello. Welcome. So how can we represent all of that? To understand how we can represent all of that, we need to understand how exactly we're passing the information through the neural network, right? So here are the inputs, X1 and X2. And here, on each of the connection, we have additional numbers. So effectively, we have 4 numbers in here. So let's actually denote them with W1. So this is the weight of this connection. Then W2, this is the weight of this one. Right, so then W3, this is the weight of this one. And W4 is the weight of this one, right? So let's denote maybe the actual values in here with A1 and A2, right? So this is the input X1 and X2, and this is activation of this specific neuron A1 and A2. That's why it's called A, So how we compute A1 and A2, right? So how do we compute them? So A1 is equal to what? Right, so we take X and multiply it by the weight of that specific connection. So this is going to be X1 multiplied by W1, right? And then X plus X2, right? And then we multiply by this connection, by W3, right? So this is W3. So, okay, then we also have to add a bias in here. So we also add a bias in here. So then we need to compute A2, right? So we need to compute A2. And for A2, we also have X1. So as you can see, it's like a similar thing in here, multiplied by already different connection, different weight, W2, right? So this is W2, plus X2 multiplied by W4, right, multiplied by W4 plus B, but it's actually B1 and B2, so this is B1 and this is B2, and this is how we compute these two activations in here. But here is an interesting thing. Don't you notice something interesting about this stuff? Don't you notice? If you have a background with linear algebra, who has a background with the linear algebra? They can probably notice something interesting in here. They may notice that specifically, at least this part, excluding the biases, right? Excluding the biases, looks like a matrix multiplication. It's sort of like it's a dot product and matrix multiplication. So can we just take these values like x1 and x2, w1, w3, and like express them in terms of matrices? Right, so essentially we can say, okay, the input is going to be a matrix x1 and x2. So a single matrix represent my paint fucking crashed! Anyway, so oh my god, thank you so much. Recover and save. We're saved, chat. We're saved. Oh my god. So let's call it something like NN aura. Oh my god. Okay, so I hope it's yeah, there we go. All right, that's totally fine. So I don't know what exactly happened, but we're totally safe now, so everything's fine. Okay, so reliable software in 2023. How about that? Reliable software. Thank you so much. Right, if I had money, I would probably donate to MyPaint. Unfortunately, I don't have any money. So okay, let's actually define this matrix. So it's going to be x1 and this is x2, right? So this is the sort of like an input matrix that represents the input for the neural network that we're passing through the neural network. Right, so to create this sort of effect, what we have to multiply it by? What kind of matrix do we have to multiply it by? Right, so it's definitely going to be matrix 2 by 2. Right, so it's going to be matrix 2 by 2, and it's going to be a matrix of the weights of the corresponding connection, right? So it's going to be the weights of the corresponding connection. So we'll need to come up with the indices properly in here, right? So usually I like to think of matrix multiplication as sort of like this cross product of the things, right? So essentially if you have, so this is a matrix 1 by 2, right? So this is a 1 by 2 and 2 by 2. So the general sort of like a rule that you memorize, right, is that you can only multiply the matrices where their inner size is equal, right? And it's quite important to remember that this is the amount of rows, right? So this is the amount of rows and this is the amount of columns, right? So why it is important? Because usually we think about the coordinates as x and y, but x is a horizontal one, it's a columns. X is a columns and y is rows. But here it's the other way around. So first come the rows and then the columns, right? So it's quite important. And they're only multiplicable when their rows are equal, So otherwise, the multiplication between such matrices is not defined as far as I know. And the final result, the result of the final matrix is going to be 1 by 2. So it's going to be like basically outer sizes, right? So it's going to be the outer sizes. So if this thing was something like 5, the final result would be 5 by 2, right? But this one is 1, so it's going to be 1 by 2. So that means this entire thing is going to be similar to this matrix, right? It's going to be something like A1, A2, right? So that's basically this entire multiplication, and that's basically what we want to have in here. So as you can see, this is the input for the neural network. These are all of the connections, right? There is 4 connections in here. These are all of the connections, and when we apply them together, we're sort of like passing this information through the neural network, right? But this entire thing doesn't really take into account the biases, because one of the things you have to do in here, right, is add the biases. But it's actually very easy to take into account. I think it's just basically you do plus the vector of biases, and vector is just basically a special case of matrix, right? So we're going to use these terms sort of interchangeably, and this one is going to be A1 and A2, right? So A1 and A2, right? And this is basically like a passing information through the neural network. You have this signal, you pass it through. Here is the weights, and here is the biases. So the main problem here, as I already said, is this like what are the indices in here, right? The way I like to think about matrix multiplication is that I put the left matrix here usually, right? So I put the matrix in here, the first one. The second matrix where I put it in here. So this is the second matrix. So I put them like that. And the way I multiply them is just I basically find the intersection of this row, right? So this is this row and this column, right? And that intersection creates the element, this like element of the final matrix. And how you do that, you basically multiply these elements together, right? Right, and add them to here. Then multiply these elements together and add them to here. And this is one of the reasons why their inner sizes has to be equal, right? So because here's the columns and here's the rows. Here's the columns and here's the rows. It is impossible to combine them together if their internal sizes are not equal, right? So this is where this requirement is coming from. Right, because you need to sort of like intersect these entire things like together, right? And this in this specific case, right? So this one is going to be like A1, A2, and this is going to be W's, right? And what do we do in here? So A1 multiplied by W1, so that means, right? W1. Actually, it has to be X. I'm sorry, I already, you know, being tied x1 and x2, right? So x1 multiplied by w1 and then w3, right? So that means right, so that this column is 1 3 and this one is 2 4, and it actually fits perfectly. 1 2 3 4. Okay, that's perfect, right? So the reason why I was actually like demonstrating all of that is because I wanted to come up with the like with the correct indices in here, right? So because it's kind of difficult to not screw this stuff up. Right. So, but essentially, people usually index those things in a completely different way. They usually index them as the, you know, as they usually index them the matrix, right? So 1 1. This one has to be 1 2. Right. This one is 1 2. Right. So this one is 1 2. This one is 2 1 and 2 2. So because of that, this one is 1 1 1 1 2. Right, 1 2 2 1 2 2 2 1 2 2. Right. I hope I didn't make any mistakes in here. Yeah, that's basically what it is. Right, and on top of that, by the way, there is also an activation function, right? So there's also an activation function. Basically, you have to like apply, for example, sigmoid or ReLU to each element of the final matrix in here. So we can say that after you did all of that, you just like put this activation in here, and that's basically how you pass a single through a single layer, right? right, through a single layer. Yeah, so and then when you want to pass this final thing through another layer, right, you would have to do the same thing. There will be a matrix of weights in here, so there will be some weights in here as well. But this time, this thing is going to be how many of these things? Right, if we have this thing 1 by 2, and we want a final thing to be 1 by 1, right? So the matrix of weights is going to be 2 by 1, right? So 2 by 1. So that means you would have to take A1, A2, right? So this is the activation from the previous layer. Then you would have to multiply it by the weights, these specific weights in here. This one is going to be something like V1 and V2, right? Something like this. Since it's 1 by 2, 2 by 1, the final thing is going to be one single number. You would have to add a single bias in here. So this is going to be a matrix of a single element. I'm not sure if that's how it works with matrices, but anyway, right? So then you apply the activation of this entire thing, right? You apply the activation and you get the final output of the neural network. Right, so essentially the simple form of passing a signal through a single layer looks like this, right? We can even sort of like, you know, simplify this entire thing. So the matrix of activation could be just A multiplied by the matrix of weights plus the matrix of biases, right? Plus the matrix of biases plus some sort of activation, right? And you basically keep repeating this thing through each individual layer, right? Through each individual layer until you went through the entire neural network. And that way you can actually create like a fully connected neural networks of different architectures, right? Of absolutely like arbitrary architectures. So maybe you can have like 3 inputs in here, right? You have 3 inputs in here, 2 inputs in here, and maybe 4 inputs, 4 you know, neurons in here, and maybe 1 in here. Right, so and essentially all of the connections are going to be something like this, right? Something like this. Then all here it's going to be connected like this. Right, and this entire thing is finally going to be fully connected to here. Right, so and essentially this is going to be matrix 1 by 3, 3 by 2, 2 by 4, and 4 by 1. Right, and you have like several matrices, and you pass these signals through this entire network by matrix multiplication, addition, and then activation, right? So you also have to apply the activation function if you have one, right? So, and that basically, that simple formula, by the way, that simple formula creates basically the entire sort of like a mental framework of working with neural networks, right? So it's like a mental framework, and it's actually very convenient to think about this kind of stuff because it can create like arbitrary, complex, fully connected neural networks, right? So it only can represent fully connected ones. If you don't really want to have a fully connected one, Twitch literally disconnected me. Yeah, hello, welcome back. So Twitch literally disconnected me. My internet was fine. My internet was totally fine. It's something on Twitch side. It literally disconnected me. I think they don't like me. Anyway. So basically, right. So this thing creates a fully connected neural networks, right? It creates fully connected neural networks. And I suppose if you don't need some of the connections, the training process, right? The training process will just deactivate some of the connections, right? So yeah, that's basically how I think about it, right? I'm not a machine learning person, right? I don't really know all of the justifications about these kind of like decisions, but I personally find this like application of linear algebra for representing neural networks kind of elegant, isn't it? Like it's kind of cool, right? So that you have the signals, right, that pass through the neural network, and it's just like a sequence of matrix multiplication. It's just like it's kind of cool how it just like fits perfectly in here. I don't fucking know. Right, and what's cool is that this is just 2 matrix operations, right, these are just two matrix separations. And as far as I know, these are two very important, you know, sort of like matrix separations, to the point that there is literal hardware that is designed specifically to multiply matrices and add matrices. Right. So if you ever heard, right, if you ever heard about like a specialized hardware or people doing stuff on GPU, right, specialized hardware for artificial intelligence, like what a specialized hardware for artificial intelligence is doing. If you read about that, you would find that it's just doing matrix separations. And it's just like, what? Like, what does it have to do with artificial intelligence? Why do you need matrix multiplications and additions? What the fuck? Here's the answer. That's why. Right. And if you optimize just these two operations, like passing information through a neural network, is going to be like very fast, right? Yeah. So, and basically what I want you to do today, right? What I want you to do today is develop a simple framework in C that basically allows us to define, train, and feed forward neural networks in C. Right. So my idea is going to be the following. We're going to start developing header-only neural network library, and we're going to port our small little models to that framework, right? And see how working with these models in that framework is going to look like, right? So that's basically the idea for today's stream. Right? That's basically the idea. Isn't that cool? Isn't that epic? Right. So let's go. Ooh. The time has fucking come. Yeah, so how are we gonna call our small little framework? We're gonna call it something like, since I want it to be like a stb-style header-only library, I think I'm gonna call it an n.h. Maybe it's already taken, maybe this name is already taken, but I don't really care. I create this entire thing for educational purposes, right? So an n.h, there we go. Right, so let's create an inclusion guard, right, an n.h. So this is needed just in case you include this thing twice, right? So this is where we're going to have all of our declarations, right? So because the thing about STB header-only libraries is that they act simultaneously as headers. They act simultaneously as headers and as the C files, right? So here we're going to have a header part. And then the C part is going to be behind if defined and then implementation, right? So and if and then implementation. So this is where we're going to have all of the implementations of the declarations up there. So this is the header part and this is the C part. The way you work with all of that, so let's actually create an n.c, right? The way you work with all of that is that you include an n.h, not bb, an n.h, right? You create an entry point. Something like this, right, and by default it acts like a header, right? By default it acts like a header. As soon as you define and then implementation, it starts to act like a header plus a C file, so it will include all of the implementations into your main program. The reason why it acts like that is because it gives you control over where exactly you want to place your implementations when you compile, right? So because other parts of your other translation units probably don't want to include implementations, they just want to use this entire thing as a header because they only care about declarations, right? So that's basically STB libraries 101, right? If you ever wanted to create one, so this is how basically they operate. There is more information about how STB libraries work at the nothings/STB. So I think there is even a document there that basically describes the principles of these libraries that Sean has come up with. STB how to, right? So these are the principles, right? So I'm not going to go into them too much, right? But I'm going to put them in here essentially. I'm going to put them in here. Just a second. Okay. So I'm gonna give that thing in the description, right? So where is my description? Do I have description? Here it is. STB library principles. Right. So because it's very like not everyone knows about this kind of approach of developing things in C, because the amount of people who develop in C at all, it actually becomes smaller and smaller and smaller. Is the bot down, by the way? Oh, the bot is probably down. Yeah. So, damn. Probably. Oh, you know what that means? That means that there was problem with my internet. Yeah. That means there was a problem with my internet, but it didn't really ruin the ping, so I constantly ping the other thing. So just a second. So I'm gonna put the disclaimer in here. Fixing bot. Just a second. Right. So let me quickly do that. I need to SSH to my separate machine because the bot is running in a separate machine. Right. Actually, it's kind of interesting. It's running in a virtual machine on a separate physical machine. So first I SSH to a physical machine, then within the physical machine I SSH to a virtual machine. Right. So data center. Yeah, it is like data center. Yeah. So it's kind of dead. Right. So SSHception. Yeah. So and within the virtual machine, I actually run the bot inside of TeamUX session. So the way I actually approach that, I SSH to a physical machine, then SSH to a virtual machine. Within the virtual machine, I attach to TeamUX session, and already with the TeamUX session, I have like console open that allows me to restart something and stuff like that. Right, so I'm not going to show that just in case it shows some sensitive information, but that's how it works. You have no auto reconnect for the bot. I didn't have time to implement. I'm a professional software developer. I know what I'm doing. Okay, it seems to be working now. It seems to be working. Right. So, I mean, I'm going to implement the auto reconnect at some point. It's just like I didn't have time. Okay, so I spent all of my time preparing for epic sorting session for you guys. Right. I spent all of my time on making sure the content is good, the content is high quality. Right. So if I spend all of my time on implementing useless features for the bot, the content would be shit. So that's my justification. Anyway, so let's continue. So what we need to do, right? So since the entire sort of approach of working with neural networks in 2023 generally is based around matrices, right? So we need to have a type that represents a matrix, right? So since all of the matrices are floats, right, we're gonna just have a simple structure, right, called matrix, right? And here's the interesting thing: unlike with 3D graphics, the matrices can be arbitrary sizes, right? So we can never know how big or small the matrix is going to be, right? It purely depends on how many neurons we have in a layer and stuff like that. So the matrices could be very small, very big, they could be square, they could be rectangular, they could be just vectors, row vectors, column vectors, like anything. They could be like any shapes. Right, so we cannot hard code matrices of all of the sizes. So because of that, it has to be a very dynamic thing. Right, so I think we're going to have like a structure, right, with a size which contains rows of the matrix, columns of the matrix, and we're going to have basically a pointer to the beginning of the matrix that contains the floats, right? So essentially, we're going to allocate some array of floats, continuous array of floats, and the shape of the matrix is going to be described with these two values, right? So that's how we're going to work with all of that, right? So and unfortunately that requires like working with dynamic memory, but it is what it is and it isn't what it isn't. So I suppose one of the things we can do, we can create an operation that allocates a matrix, right? So let's create matalloc. It's going to accept rows and columns, right? So this is going to be rows and columns. And I suppose it's going to just use malloc and dynamically allocate enough floats and just give the pointer in there, right? So, but it does not necessarily have to work like that, right? So if you want to allocate floats in the static memory, you can easily do that, I suppose. You would be able to do something like, right, float, some sort of a matrix, right? So this is going to be something like this. And you're going to say 0, 0, like 1, 0, 1, right? So here is your data for your matrix. And then, right, so let's call it D for data. And then you would do what? You would say, okay, here we have 2 rows and 2 columns, right? And the data starts at D. And there we go, we define a matrix 2 by 2. But what if you meant not a matrix 2 by 2? What if you meant matrix 1 by 2? What if you wanted this thing to be like a row, a single row? In that case, you can say this, and it's gonna work anyway. Right, so basically this is just the data, and this thing defines the shape of that data. You can say that this is actually a column thing, so you say it's a 4 rows but 1 thing in here. Right, so seems to be okay. Right, so this is how it's going to work. It's kind of similar to... Wait a second. It's kind of similar to the canvas in Olive C. I mean, why not? Right, do you guys know the framework? All right, so Olive C. Right, so there is a canvas, yeah. So yeah, but instead of you know, values of the matrix, right, floats, you have uint32, but you also have width and height. But on top of that, you have a stride. On top of that, you have a stride, and stride is needed to actually take sub canvases, right? But would we need to take sub matrices at some point? I mean, is it really needed? Maybe. Wait a second. For instance, imagine that you have a training data, right? And let's say that the training data is like this. The first 2 elements in here is 0, and the second one is 0. So let's actually create the training data for the OR gate, right? So here is going to be that, and then it's going to be that, and this is going to be that. So, and what if you at some point want to split this entire thing? What if we want to split this entire thing into 2 matrices? So this is going to be the first matrix, and this is going to be the second matrix. Right, this is going to be the second matrix. How can we do that? Right, so we can say that this data input, it starts at ES, right? So the amount of rows is going to be 4, the amount of columns is going to be 2. But we also need to define how far you need to jump to get to the next row. So you need to specify the stride. And the actual stride is going to be actually 3. Right. So that way, you sort of have the inputs and then the outputs. Right. In case of the output is going to be this matrix. So that means you have 4 rows, 1 column. Stride is still 3, but you start not at 0. You start at here, so the element 0, 1, 2, you have to start at 3. Right, you can even do something like this. Yeah, so you just define the continuous data and you just like split it into matrices or something like that. Why not? So, but I don't really want to go into that because I'm not really sure if it's going to be needed that much, but it's an interesting idea to think about, right? What do you guys think? Right, I think it's kind of cool, right? So, so let's continue. So we need to do matrix allocation, right? And the 2 main operations are going to be matrix dot, right? So we're going to do multiplication between the matrices. Right, and matrix sum. So, but I need to think how we're going to organize the arguments of this entire stuff, right? Since the matrix is a very much like dynamic thing, I don't want to return a new matrix, right? So I don't want to do things like this, where you accept these 2 matrices. These are immutable arguments, and it just creates a new one, right? I don't want this thing to be allocating memory because I don't really expect that, right? So if something allocates memory, I need to expect it doing that. Like, for example, in case of this specific function, right? Maybe because of that, this operation is going to accept 3 matrices, right? 3 matrices. So essentially you pre-allocate the memory for all of the 3. You make sure that their sizes fit and everything, right? And we basically iterate through these matrices and multiply them in here, right? So that way none of these functions will do any memory management. So you do all of the memory management up front, right? So I think that's how I want to go about that. But to be fair, the destination into which we're multiplying things, I would like to put at the beginning of the function to make it kind of similar to functions like memcopy, right? You know what I mean? So there's a memcopy, where you copy one thing into another one, right? And the destination is usually the first element, right? So the destination is first and source is the second one. And it's kind of consistent across some of these string functions in C, right? Memset also accepts the destination as the first element and stuff like that. So because my mental model thinks about these operations like in terms of C library, I think it would be easier for me to have the destination sort of as the first element, if that makes any sense, right? So right here, these two things are immutable, and this is the destination, right? So, and I don't even need to accept this by a pointer because I already have a pointer to the elements inside of the structure. So the structure itself is already a very lightweight pointer, right? So here's the thing, matrix as a structure is very lightweight because it consists of only 3 64-bit integers. 64-bit integers. The first 64-bit integer is rows, columns, and the third 64-bit integer is a pointer to the beginning of the data of the matrix. So the structure itself doesn't contain the data, right? It doesn't really contain the data. Right, so, and similarly, I want to do something similar for the sum, right? So when I add matrices together, right, so this one is going to be destination, right? So maybe I'm going to even call DST. So this is DST, and I'm going to. So A and B, we multiply this entire thing into DST, and then the sum, right? Question, what if size T is more than 64 bits? Does it grow in bit size? Size T is not bigger than 64 bits. I'm operating on the architecture x86-64 Linux, and on this specific platform, size T is 64 bits. It is 64 bits. So it could be on some of the platforms 32 bits, but these are very much like old legacy platforms and maybe something in embedded, but I don't really plan to run this thing on embedded. So here's the interesting thing. This thing is for educational purposes only. So that's why I'm making it work at least on my machine. The problems on other machines that may occur are not of my concern as of right now. So first thing I'm trying to do, I'm trying to make it work on my machine and my machine only. On my machine, it's 64 bits, totally fine, right? So then, once we have something working on my machine, we can look at it and think, okay, how can I run it on other machine? Oh, it creates that little problem. Let's fix the problem. Okay, it runs on 2 machines. Okay, let's try to run it on the 3rd machine. Oh, it doesn't have any problems because that's all the problems there are, so it can run on 3 machines. So that's how software development works, right? So you don't try to solve all the possible problems, even non-existent ones, simultaneously. This is not how you do that, otherwise you're never gonna go anywhere. Okay, so now, that's the only operations that I care about right now, at least, right? So this is what we're gonna have right now. And one of the things I probably want to have is something that prints the matrix, right? Because I want to be able to see the matrix that we just created, right? So let's create something like print. And let's go ahead and implement all of these operations, right? So why the fuck not, right? So that's the only thing we need in here. Okay, so when I'm allocating something, this is gonna be just that, right? So should be pretty straightforward. So essentially I can set the rows to the rows, right? So then the columns to the columns, and then when I need to allocate the elements, I'm just going to do malloc, right? I need the size of a single float, right? So the size of a float. But maybe I'm gonna make the type that we're using here sort of like a variable. Maybe it's gonna be type def, because maybe you want to use double, or maybe floats 16. Or something like that. So because of that, I want to do the following trick. I'm going to take ES, which is the pointer to float. I'm going to dereference this entire thing, and I'm going to take size of that specific thing. That way, if I ever change this type to double, I would never have to go down there and change anything in here, right? Because if I would just say the size of float, if I change it to double, I should not forget to go in here and switch it to double. If I do something like this, I never have to do that, right? I can just switch that to a different type and it will work automatically. right? So this is the size of a single float, then I multiply it by the rows, and then I multiply it by the columns, and this should allocate enough memory for all of these floats. And we're gonna assert that this entire thing is not equal to null, right? And after that, we're gonna just return this entire thing, right? As simple as that. So what about dot operation, right? So I suppose I'm gonna postpone implementing dot operation because it's a little bit complicated. Right, so, and sum operation also, let's postpone that. So void dst a, and here print, we don't really do anything. So essentially, I just want to try to compile this entire stuff and see. Okay, so let's create maybe a build.sh script that is going to build the example for us. I just realized that I probably have a bunch of subs that I didn't acknowledge, actually two. Team Scar, thank you so much for Twitch Prime, and Aponetry, thank you so much for tier 1 subscription. Thank you, thank you, thank you. All right, so let me see. So I'm going to create a build.sh, and then what we're going to do, we're going to do clank wo w extra o nn.c. We also probably want to link with lm, and there we go. So I'm also going to actually enable the tracing and stuff like that. Let's make this shit executable, and boom, boom. It doesn't even freaking work, right? Because we don't have a size t. So size t is defined somewhere, I think, in std-def, right? So that's the place where all of the definitions go. Malloc, all right, malloc is defined somewhere there. So here's an interesting thing about stb-style libraries is that usually they provide a way to customize the allocation, right? So usually you have some sort of a macro called nn malloc, right, which accepts the size. Well, in here we can say that it's equivalent to malloc, right? It is equivalent to malloc. And what they do is, if we only define this thing if it was not defined already, right? So by default, right, it's gonna use malloc, right? And malloc by default is gonna use malloc, but then when you include this entire library, you can very easily say, okay, and malloc is my malloc, which actually allocates the memory completely differently. Maybe it doesn't even call to libc. Maybe you have a pre-allocated pool of memory and you just linearly allocate that. So essentially, the cool thing about the stb libraries is that they give you more control over how you allocate your memory, right? And I kind of want to mimic that as well, right? So, and that also sort of decouples all of that from libc, just in case you want to run this library in an environment where you don't have libc. And you may think is that, well, this is embedded, right? Like, do we want to run an embedded? Do we care about embedded? But this is not necessarily true. There is a couple of platforms where there is no libc. Well, I mean, for example, in WASM by default, there is no libc, right? But there are implementations for libc. There's also WASI. They're a huge pain in the ass to work with, right? So it's just like, and sometimes the pain is so huge that I feel like sometimes it's just not worth it. But for some people it's worth it, right? But for me, usually it's not worth it. Every time I'm programming in C and I'm writing like a WASM application, I literally don't use C. I just cannot. I'm too dumb to use mscripten. Like every time I open Inscripten, I try to follow the tutorials. This thing is so lousy. It's just like it falls apart right in my hands. It starts spitting out errors. I have to go Google, ask ChatGPT and stuff. Like, I just don't want to do that. Let's reduce the complexity, get rid of all of this shit, and keep it as simple as possible. And it just works. It's beautiful. Right, so I don't know. So people who are way smarter than me can deal with all of that madness. I cannot. I'm a very dumb person, right? So I like simple things. I like to keep things simple. It's just like, yeah. Sorry. Sorry. Okay, so we'll get a bunch of more subs. Thank you so much. Eponetry, I think I already acknowledged that. Dr. Stud, thank you so much for Twitch Prime. And Tinted Trunk, thank you so much for Twitch Prime as well. Ooga Booga development. Yes, so I'm an Ooga Booga developer. So yeah. Okay, so we're not going to have our own malloc. What I want to do is just like a run build.sh, and let's go to the compilation. So this has to be an if, and also assert, right? So yeah, implicit declaring library. In this case, we can actually also include std-lib, right? Because we know what we want this thing from. And assert is also often customizable if not defined. And then assert, we're gonna just include assert.h, define, and then assert, and it's just like literally the same assert in here. Right, and it's very useful, again, for example, in WebAssembly environment, where you probably will implement your own assert if you don't use libc or something like that, right? So, and let's just do it like this. Okay, cool. So, and how are we going to be using all of that? Right, so let's create a matrix, and let's define a matrix of alloc 2 by 2, right? So alloc 2 by 2. And then I'm going to print this entire matrix just to see how it looks like, because I'm really curious at how it does look like. So did I call it something else? So mat print. Oh yeah, I forgot to accept a matrix that I want to print actually. So all right. So there we go. That's a poggers. Right, if we try to run this entire stuff now, right, so if I do build and n, it will not print anything because mat print is not implemented. Okay, so how can we implement mat print? So we need to start iterating rows and columns, right, so as usual. Right, less than m rows plus I, then this is going to be j, this is going to be columns, this is going to be j. And let's literally just print all of these things in here, right? Let's just literally print them. And here's an interesting thing. So ES is just like a pointer to the linear memory, right? So, but we need to interpret it as a two-dimensional array. So that means, right, we have to do some very scary shit. We have to take the row, right? And we need to skip I rows. What's the size of the row? The size of the row is the amount of columns. Does it make sense? Right, this is actually a mentally difficult thing to imagine, but imagine that you have something like this. This is a single row. You have 4 rows, right? So what's the size of that row? The size of this row is 4 columns, right? So the length of the row is the amount of columns, right? Does it make sense? Right, so that's very important. So we need to skip I rows, so that's why we have to multiply it by columns, because that size of a single row, right? And then we have to offset it by j columns, right? And that's very much error prone, right? So you may actually confuse some of the indices, and it's just like, it's very dangerous. I don't like to do these things like that. Right, and because of that, like usually in C, I don't have much choice, unfortunately, right? I don't have much choice. I like to define like a macro that does this kind of stuff for me. So essentially, I want to make something like mat at, right? So it will accept the matrix, row and column, like I and j. So, and essentially, I'm just gonna, you know, turn it into a macro for me, right? And it's gonna work like that. But here's the problem, right? So m, I and j could be an expression, right? For instance, if you put mat at m I plus 1, right? The I is going to be literally replaced with I plus 1, and this is not a correct expression. So in macros, what you usually do, you actually wrap all of the arguments in parentheses just in case they are complicated expressions that will ruin this entire thing. Right, so you have to be careful with this kind of stuff. But I mean, it's a macro, usually you don't look inside of it, so it looks a little bit ugly, but that's fine. Right, and instead of like doing this kind of stuff, right, instead of doing this kind of stuff, I can now do mat at m ij. And I don't have to think about any of that stuff, right? I don't have to think it's a row size column, what? Okay, the element at ij, I is the rows and j is the columns, that's it, right? All of that madness is actually tucked away nicely under this macro. I don't care about it, right? So I don't really care about it. Unfortunately, like in C, you have to do this kind of tricks, right? So in better languages, you would probably use something better, maybe like operator overloading or something like that, but in C it is what it is and it isn't what it isn't. So we drew a single row, and then at the end of the row we want to put some sort of a, like a new line in here. So, and that's how we're going to be printing the this thing. So And of course, we have this kind of interesting thing, printf. So maybe we want to include stdio. So we just allocated a bunch of memory, and this is basically 2 by 2, and yeah, that works nicely. That actually works nicely. So what if I define like 1 by 2, right? So this is a single row, 2 by 1. This is a single column. What about 10 by 10? 10 by 10, yeah, that's a matrix 10 by 10. So everything seems to be working nicely. All of that is 0, right? One of the things we probably want to be able to do, we want to be able to randomize the matrix, right? Because that's how we usually initialize the neural networks. We just randomize everything. So maybe because of that, I want to create a function. Right, so here we created this thing, matrand. It's going to just accept a single matrix and just randomize this entire stuff. So let's actually go ahead and do that. Right. So we've got some subs. I can see subs. Money. Trimo, I hope I pronounced your nickname correctly. Thank you so much for tier 1 subscription with the message ML and C. All here for it. Well, yeah, ML and C. It's actually very simple because, like, neural networks specifically is just matrix multiplication. And believe it or not, all of the specialized libraries for matrix multiplication and addition and stuff like that are written in C anyway. Whatever NumPy or TensorFlow or whatever people use there, all of that is written in C. So maybe you're using it in Python, but it is just like a thin wrapper over C code anyway. All of that is written in C anyway. It's kind of funny how people are surprised. You're doing like a machine learning in C. All of the machine learning is done in C. All of it. 99.99999% of it is done in C. Sometimes in Rust people do some stuff, right? But all of that is like, Python is just like a wrapper, just a glue code. It's just a glue code. So yeah. Anyway. It's all bytes. Well, maybe. Anyways, so let's actually randomize this entire thing. So, and by the way, so once we implement this framework, we may want to actually slap some functions that speed up the matrix multiplications and additions and stuff like that. I think we could try to use LAPACK, right? If I remember correctly, that specific thing had... by the way, I didn't remember. I think they banned my IP. Yeah. Okay. Yeah, I cannot visit this thing. I remember. Yeah, I remember. I cannot visit this thing. They probably banned my IP. So, but I can visit it over VPN or Tor, right? So they didn't like me. So anyway, why? I don't know. I don't know. That's a very interesting question. Why? Why half of the internet is banned for me? I don't know. All right, so let's do the following thing. So we need to randomize all of this stuff, right? So it's going to be M, I, and J, and we're going to just do rand float, right? So this is going to be the function that I use all the time, right? So I think we can make it part of the framework here as well, right? So float rand float void. The fun part of my reality is browsing internet from time to time and see occasional fuck you and UAP. It's actually quite funny, to be fair. Anyway, so what we have to do in here, so it's going to be rand float, and we're going to define this entire thing rand I think max, right? And the way this works, it will return a random number from 0 to 1, right? Random number from 0 to 1. So, right, and so here's an interesting thing. What if we want to initialize the matrix actually within a certain range, right? Not just 0 and 1, but like a very specific range. So I usually like to specify that range in here. So this is going to be low and this is going to be high. Right, so it's going to initialize this entire thing like in that specific range. And essentially what we do, we multiply it by high minus low and just add low. Right, and that can assume that low is less than high, but if you do the other thing, well, you'll just get garbage, right? So, but nothing bad is going to happen, right? Nothing bad is going to happen, so I think that's fine. We're not going to do any additional checks in here, I think. Right, and I think they're very much necessary. Okay, so then here we're going to do mat rand, and there we go. So that's kind of nice. So we allocate the matrix 10 by 10, we randomize the matrix, and we're gonna print it. So let's see how it's gonna look like. Well, I mean, we have to randomize it with like, let's say from, I don't know, from 0 to 10, right? So that's gonna be the values that we want to randomize all that stuff with. Let's go through the compilation errors. Correcting types, I suppose, mat rand. Yeah, so we have to have a different, yeah, there we go. Look at that. So this is a random matrix with values from 0 to 10. That's pretty convenient. But it's going to be the same random values, right? Because we don't really initialize the seed, right? So we need to set the God seed, right? So we are setting the God seed, and that requires including the time. Right, there we go. So as you can see, God seed works every second, right? So God seed updates every second, because the time returns you seconds. All right. So cool. That's pretty cool in my opinion, I think. So let's go ahead and implement some stuff, right? So the easiest thing to implement in here is sum. You just need to add two matrices, but you can only add the matrices if the shape of the matrix is the same, right? So you can only do it like that. So we probably want to do assert, right? That the DST rows is equal to A rows, right? And also correspondingly the columns, right? So we want to check that. After we check that, right, so essentially what we can do, we can start iterating this entire stuff, right? DST rows plus I, and then J. Since the matrices are very much dynamic, we can't really check the shapes of the matrix at compile time, right? It's very much runtime thing. Right, so, and let's go ahead and do that. DST IJ, and we do addition, so it's plus mat at A IJ. There we go. So that's the addition, right? So that's the addition of this entire matrix. Isn't that poggers? Isn't that poggers? I think it's pretty freaking poggers. So we probably maybe want to test that somehow. I don't even know. So we can allocate a bunch of matrices, right? So let's say that we're going to have a matrix 2 by 2, right? And let's keep it sort of like 0. And then we're going to have another B, right? And we probably want to fill the entire matrix of B with sort of like ones, right? So maybe you can do matrix fill B and yeah, 1. Okay, so maybe we also want to fill it with ones here, right? And we want to print A, right? Then we're going to print something like this in here. So we're going to separate this entire thing. Then we're going to do matrix sum A and B, and we're going to print this entire thing yet again, right? So here we just allocate this entire thing, fill it with ones, this thing, fill it with ones, print A, add them together, and then print the A again, just to see if this entire thing works. That will probably require implementing something like matrix fill, matrix M. I'm not sure if I'll ever use that operation ever again, but it's probably nice to have it anyway, I suppose, right? Though it's kind of similar to just mat rand, right? Because essentially what you do is just instead of random value, you just put X in there and that's it. Right, so that's basically what it is. And yeah, there we go. So this was A, then we added another thing in here, now it's B or something like that. So yeah, that's cool. So we have addition for the matrices, we're almost there. The framework is almost finished, right? As soon as you have these two operations, dot and sum, you basically have a neural network framework. I don't know why you need a TensorFlow that takes like, you know, 24 hours to build, how many times it requires you to build. It's just like it's two matrix operations. Right, I don't freaking know. So it's so simple. Haha. Okay, so here is an interesting thing. Right, so matrix multiplication is not defined unless the inner sizes are equal, right? The inner sizes are equal. People say something, I'm wrong with index j. No, I'm not. You're looping rows twice. Where? Where I'm looping rows twice? On which function? On which function? Okay, so if chat basically debates me. Okay, so they didn't debate. Okay, so this is a close. Okay, I see. Thank you. Right. Anyway, whatever. Okay, so what I was doing, I was explaining something important. I was explaining the matrix multiplication. Right, the inner sizes has to be equal, right? So this is going to be assert A, so first rows, then the columns, right? So we have to say that the columns are equal to the rows of B, right? So essentially, if we have matrix 1 by 2 and 2 by 3, right, they're multipliable because their inner sizes are equal to 2, right? And so this is the columns and this is the rows. This is the columns and this is the rows. Very important. But most importantly is that the size of the final matrix is going to be the outer sizes, right? So the final matrix is going to have 1 row and 3 columns. We also want to check that. The final matrix is DST, right? So that means that assert DST, the amount of rows, is the same as the amount of rows of A, right? So this is the amount of rows in here, and the amount of columns of this thing is 3, which is the amount of columns of B, right? So it's like a little bit symmetrical, right? It's a little bit symmetrical. And essentially when we do this sort of like a you know, intersection thingy, we are iterating the destination table, right? So each point in here is the point in the destination table, so that means the 2 outer loops are gonna be over DST, right? So this is gonna be size t less than DST rows, right? Plus I, right? Then for size t j DST columns plus j, and within that loop, right? Within that loop. Here we iterating the inner sizes, right? So since the inner sizes are the same, we're iterating that inner size, right? So that specific value. So once we check that these two values are equal, we may probably take that value, the value that is equal, and just put it into a separate variable, so we can use that variable inside, right, when we are iterating the corresponding row and corresponding column of these two matrices, right? So we can do something like size t, k less n, right? So n is specifically inner size, plus k. There we go. So, and the value of the destination matrix of I and j, because again we are iterating the destination matrix, right? So initially it is going to be equal to 0, right? Initially it is equal to 0, and what we're adding, we're actually adding the multiplications of these elements. So the product of these two elements plus product of these two elements, and so on and so forth, right? So the first element is matrix A, I, K, multiplied by the matrix B, K, J. Right, and look how we are determining the coordinates of this element. Their inner sizes are the same. So the first one is IK, the second one is KJ. Right, and K iterates the inner size, and that's the this is where we use that key, right? This is where we use that key, and that corresponds to the requirement of the inner sizes to be equal to each other, right? So that's one of the reasons why they have to be equal, because we're iterating that inner size, right? It's kind of important, right? And the rows and columns are outer things, and the outer things, this is where we're iterating. And that's the entirety of the matrix multiplication, believe it or not, if I didn't make any mistakes. That's basically it. Right, that's basically it. So we're just like accumulating this entire thing, and yeah, let's go. Isn't it cool? Does it make sense? Because people find matrix multiplication really scary, but if you think about matrix multiplication in terms of this sort of like a crossing of rows and columns, you can derive all of these things like quite easily, and you can see that this entire thing is sort of like very much symmetrical, right? So, and it kind of does make sense. All of that does make sense. All right, so this is the matrix multiplication. Okay, so what we're gonna do in here, what we're gonna do, would be kind of nice to test that somehow, but I don't know. We can have like a matrix A, which is, let's say this is gonna be, oh yeah, we can do something like, yeah, 1, 2, right? This is that, and this is going to be matrix random, right? So this is a random matrix A, and then we're going to do 2 by 2, and let's fill this one with just zeros, right? So this one is going to be just zeros, and we need to have a destination matrix, right? So in the destination matrix is going to be, I suppose, alloc 1 by 2, right? Because this one is 1 by 2, 2 by 2, the final is going to be 1 by 2. All right, so, and we can then do mat dot dst a and b, right? Dst a and b, and then we can just print the final matrix, print dot dst, and just see how it looks like. Right, so let's see if it's going to work. So something doesn't particularly work, we have to provide the values from, let's say from 5 to 10, because why not? Mat print, I meant print in here, and yep, so that basically filled this entire thing with zeros, right? So that filled it with zeros. We might as well probably mat print A and just split this entire thing by a line. All right, so this was the matrix, so we multiplied it by 0, and there we go, this is what we got. If we fill it with 1, right, if we fill it with 1, it just like, it kind of doubled it, but not really doubled it, but yeah. So I suppose one of the things we can try to do, we can try to define maybe like ID matrix, right? So float ID data, right? And this is going to be like a 4 of these things. 0, like 1, 0, 0, 1, right? And the reason why it's like that is because it's like this. And B is essentially going to be something like rows 2, columns 2, and elements is just ID data, right? So we're gonna do something like that, and that thing should actually, yeah, okay, it worked. So this is ID matrix, is just like keeps it the same, All right, so you know what that means, chat. You know what that means. We already have a neural net framework, don't we? Yeah, so because we implemented all of the necessary operations, how about it? How about that? We can try to port some of the models, right, or maybe like something like Zor model to this specific framework, right? So we can try to do that. So the question is how we can do all of that, right? Before we do all of that, I think I want to make a small break, right? Because I ran out of tea and I also streamed for almost 1 hour. So I think the time has come. And after the break, we're gonna take our Zor example, right? So where's the Zor example? And we're gonna port it to just matrices, right? So we're gonna do the same thing, the same stupid thing in here, but in terms of matrices, right? So in terms of matrices, and we'll see how it's going to go. The cool thing is going to be is that all of these things are parameterizable. So if you want to just add more layers or add more neurons to a particular layer, it's just going to be changing the amount of those things, right? That's going to be basically the idea, right? All right, let's make some break, and all right, let's try to port the Azure model to our new framework that we just created. Yes, we created a brand new machine learning framework. It took us 1 hour and 100 lines of code. Can your TensorFlow do that? Okay, I'm sorry. As we already, discussed, so the entire model consists of actually like 2 layers, right? The first layer is basically 4 weights, right? And these 4 weights are effectively a matrix 2 by 2, right? So let's allocate the matrix 2 by 2, right? So this is the weights of the first layer. And on top of that, we have biases of the same layer, right? And the biases is actually 1 by 2 because we add them in here, right? So we literally add them in here. So this is going to be matrix log 1 by 2. This is our first layer, right? This is our first layer. We can try to indicate that maybe with 1, right? This is our first layer. I want to maybe just cross it out, but maybe I can just remove all of that because I don't think it's useful in any way, right? So this is half of our model. The next layer, right, W2, right? The next layer has only 2 weights, right? It has only 2 weights, right? And how do we organize all of that? So if you have this thing, that means it's going to be 2 by 1, right? So if the activation is a single row, the weights has to be a single column, which will effectively compress the final result into a single value, right? So that means this thing has to be 2 by 1, right? It has to be 2 by 1. And the biases, right? So because there's only 1 neuron, it's going to be a single bias, but we can just say, okay, so it's going to be 1 by 1, right? It's a matrix 1 by 1. So, and this is basically the entire model, right? Isn't it? I think it is. And we probably want to initialize this entire model. We want to randomize all of these things, right? So it's going to be V1, right, and V2, V2, B2. And after that, I want to print all of them, right? After that, I want to print all of them. So I'm going to, well, when we are randomizing all of that, so it's probably going to be something like, let's say from 0 to 1. I think that's going to be fine. Then, what are we doing? I want to see this entire model. So I'm going to copy paste this random shite, and I'm going to say print this thing, please, pretty please. Boom. But here's an interesting thing. It's not going to be readable whatsoever because we don't really know the like what corresponds to what. Right, if you know what I mean. We don't really know what corresponds to what. Right, it's like, what the fuck is going on in here? Like, I don't fucking understand. So maybe we kind of want to extend print to actually accept some sort of information, but I don't know. Right, so when we're printing, one of the things we can do, we can maybe wrap this entire stuff into something like this. Right. Right, so this is going to be something like that. And let's indent 1, 2, 3, 4 with 4 spaces, right? So it looks a little bit better, maybe. So we also have to put this thing and this thing, of course. That's already better, right? That's already better. So this is the weights of the first thing, then the biases of the first thing, then the weights of the second thing, and the biases of the second thing. That's already better. We can see some shit. But we don't really know what corresponds to what. Maybe we can make matprint accept the name of the matrix, right? So let's accept the name of the matrix, so we can do something like s equal and the name, right? S equal and the name. And we probably want to modify this thing because it's C. Right, and now we'll be able to maybe even do some epic shite, like so. Yeah, so we specify the name, and there we go. So now we can see all of that stuff. Isn't that cool? Isn't that cool? I think it's pretty freaking cool. So yeah, we can clearly see everything now. So another, okay, so this one is kind of funny. Right, so it puts a lot of, though it's kind of nice that it actually puts so much space in here, I think. Right, I think it's kind of, I'm gonna keep it like that for Right, so it would be kind of nice, like, if I didn't have to provide this name somehow. Right, we can always do something like mat print. Right, and let's accept the matrix in here, and let's just forward it to mat print. But also, in C preprocessor, there is a very cool thing where you can take the input token. So this is actually a collection of tokens, and you can say, okay, stringify that, and it will turn it into literally a string literal. That way, you can just do something like this, right? And effectively, it will do that for you. Yeah, there we go. So, and no matter what kind of expression you put in here, you can actually do something weird. Like, you can take a pointer to this thing and then dereference this pointer, right? And it will actually include taking the pointer and dereferencing the pointer and use it as a string in here, right? So we can put like an entire expression in here just to sort of like indicate what exactly we're printing in here. And this is rather actually convenient. We can actually make it like a part of the framework. Why not? Who said we can't do that, right? So it's just like an additional thing. Right. Can your TensorFlow do that? I don't fucking think so. I'm sorry. Like, I hope it is obvious that I'm joking. I hope it is obvious then when I say this stupid shit, I'm joking. Because here's the thing. I quite often cut out these kind of moments when I say some stupid controversial shit on Twitch, and I post this clips on Twitter, and there is quite a few people on Twitter that come to me to tell me, dude, this is so fucking dumb, you fucking, like, what the fuck you saw? It's just like they're fucking triggered or something. It's just like, isn't that obvious that I'm joking, right? Or this is something specific to people using Twitter. Like, I don't fucking know. I think this is something specific to Twitter, right? Because sometimes it's just so fucking funny. Yeah. And the Twitter makes you question, are you, like, is it really obvious that you're joking? Or maybe, like, I'm just saying that too seriously to the point that people cannot tell that I'm not joking or something. It's just like, it's probably Twitter, right? So, yeah. I should not probably think too much about shit I see on Twitter. Twitter is very, very dangerous. Anyway, so we've got some sub. I think I didn't acknowledge Nazriel X. Thank you so much for tier 1 subscription. Thank you. I'll read. Like when you posted the teapot implementation with twinkles. Yeah, exactly. I made a tweet where I said if you write tests that you're weak and don't trust yourself, and have gotten 50-100 replies telling me that they write tests to make sure things don't break. Yeah, you can't joke on Twitter. Like, it's just like Twitter does not allow you to do that, right? So just, right. So let's continue. Anything said on Twitter loses its constant immediately as soon as posted on Twitter. Like, you cannot have context on Twitter, like, at all. All right, so we've got this thing. So the question is, how do we even forward information in that neural network? Like, how do we even do that? So since forwarding information is actually matrix multiplication, we need some sort of a matrix that represents the input, right? So let's actually call it something like X. Right, and yeah, we'll already call it X, and it's 1 by 2, right? So here is 1 by 2. Let's do matalloc 1 by 2, and this is where you're gonna put your sort of input. So forwarding, right? So how would you do that? So mat at row 0, X row 0, 0. Let's put 0 in here, and maybe 1 in here, right? And to forward that information to the next layer, you would need to multiply that by W1 and add B1 and then sigmoid F, this entire thing. So this is more of a pseudocode, right? It's not going to work. This is not how it works. Excuse me. But here's an interesting thing. We need an intermediate matrix into which we're going to be multiplying things, because I already said multiplication like requires you an intermediate matrix, right? So because I don't want mathematical operations to do any memory management. I want to be all of the memory management to be concentrated in a single function, right? So this is the only function that does any memory management. The rest of the things don't even allocate anything. So this is to keep things in control, so to speak, if that makes any sense, right? So that means that we need an additional sort of like a matrix, another matrix, right, for the first activation, right? So this is going to be, let's call it A1, right? And this is going to be the matrix for this thing, right? So this is going to be that. So matrix alloc, and it's going to be 1 by 2, right? And this kind of represents like the full layer. So the layer not only will contain the weights and biases, it will also contain the sort of intermediate activation things, right? Intermediate activation things. Right, so, and if I want to forward something, I'll have to do mat dot, right, the activation, and I'm multiplying x by w1, right? So that's what I do. And as far as I know, A1, right, A1 has the same size, has the same shape as B1, as the biases, right? So there's the same. I actually swapping them, like swapping them out, and the only thing that changes is the letter in here, right? So that means now I can do another operation, mat sum A1 B1. Right, there you go. So here I set up the input, right? I set up the input and I passed X through the first layer. I passed X through the first layer. The only thing that is left to do in here is to iterate through all of the elements of A1 and activate them, meaning apply sigmoid on them or any other activation function, right? So let me try to do that. So maybe we're gonna have, I don't know, first of all, we need to have a sigmoid, right? Sigmoid f, float f, and we're going to accept it. So sigmoid is a function that takes any value from minus infinity to plus infinity and squashes that to a range from 0 to 1. Literally, that's everything this function does. So the closer your value to the minus infinity, the closer the value of sigmoid is going to be to 0. The closer the value to the plus infinity, the closer the value of sigmoid is going to be to 1. Right? Whatever value you put, it's going to be basically from 0 to 1. It doesn't matter. Right. So which is very useful for neural networks. It has its own problems when you start doing backpropagation, but we are not doing backpropagation yet. So that's why we don't care. Right? That's the way to address problems of vanishing gradient. Just don't fucking use backpropagation. I mean, yeah, it is slow. Just buy more computer, right? So buy more compute. Who cares? Just convince Microsoft to give you like $1 billion or something. I mean, it worked out for OpenAI. Infinite descent, yeah. Okay, so and the formula is rather simple. I think it's like 1 divided by 1 plus exponent minus x. I think that's basically what it is, right? So that's basically the sigmoid. And the thing we want to do, we want to have a special thing that activates the matrix, right? So I'm thinking, so I'm gonna just probably call it mat sig, right? So, and essentially it's very simple, right? It's gonna iterate through all of that and apply that function there. So let's go. Over m rows plus plus I, and then for size t j less than cons plus plus j, right? Mat at mij sigmoid, just the same element in here. There we go. So regardless of the shape, it's gonna just go through all of the elements and just apply the sigmoid on them. So when we're gonna have more activation functions, I think I'm gonna try to abstract that away somehow, and we'll see how we can do that. Also, when we're gonna start doing like a proper gradient descent with backpropagation, so having like a variety of activation functions is going to be kind of difficult because different activation functions have different derivatives, and derivatives of activation function, it makes code not really flexible, right? So because they're kind of bake a specific formula into the algorithm, but we'll see what we can do, right? We'll see what we can do. So we're gonna have a separate stream for backpropagation and stuff like that. Okay, so we do that, and after that we want to do a mat sig a1. There we go. So this is a single path through a single layer, right? So we had essentially input x, we passed it through the first layer, and we got a1, right? We got a1. So now what we have to do, we have to take a1 and pass it through the second layer. And what is the second layer, right? So the second layer is this thing. But again, to pass it through, you need another intermediate sort of matrix, because it's actually going to be one by one matrix, because it's a final thing in here, right? So because of that, this matrix is not going to work for that, right? So let's just allocate a2 mat alloc, and you can kind of already see how you can create an abstract representation of a neural network, right? So because I'm doing that explicitly. So we can clearly see how you can abstract that away into more like higher level structure, right? So because essentially neural network is going to be array of weight matrices, array of bias matrices, and array of this intermediate activation values matrices, right? So, and once you have that, you can just like have a very abstract algorithm of forwarding and backpropagation and stuff like that. Okay, so let's go. So it can be one and yusu. Okay, so mat dot, so a2, we're gonna take the previous activation from a previous layer, apply the weights of the current layer, right? There we go. Then we're gonna apply the biases for the current layer, and then we're gonna activate a2, and there we go. So essentially, here was the input. So axis, we pass the axis through the first layer, then we pass it through the second layer, and at the end we got the final result, right? We've got the final result, and A2, as you can see, we allocated as matrix one by one, right, is the final result. Since it's a ZOR neural network, right, two values got compressed into one, right? So, and you can get that final value. Since it's a one by one, you can just like literally take the element from here and just like dereference it, and this is basically your Y, right? If essentially you have values x1, right, 0 and x2 1, you put them in here 1 2, you follow this entire process, and y is going to be here, right? Y is going to be here. So we can even maybe abstract that away to a separate like a forward function, but that separate forward function is probably going to accept this entire model, right? Is going to accept this entire model. So maybe it makes sense to maybe create a structure in here. So let's actually call it SOR like that. And maybe we want to define all of these variables in here. So you can think of the X layer as just like also intermediate activation matrix. So maybe because of that we can call it A0, right? So this is going to be sort of like A0. So this is the first one, right? After that we have things like B1 and B2. One of the things we can do is just like this, right? So this is the first layer. We can clearly see that, the first layer. And the second layer is just like this too, right? And if you want to add another layer, well, you know what to do, right? So you just add another thing in here, but then you'd have to take the shapes of these matrices, right? So, and so the cool thing here is that it's super easy to just stack layers on top in here. And again, so you can clearly see how you can simplify all of that. You can turn all of these things into arrays, right? You can turn all of these things into arrays. So now it becomes super flexible, but we're not going to make them into arrays yet, right? Because we want to like have a working model first, and then we'll see how we can improve all of that. So okay, so let's basically create a model M in here, right? And for all of these things, we're going to initialize it like so. Boom. So this is going to be ZOR, and this one is probably has to be like A0. Then we need to initialize these things So the intermediate activation things don't really need to be randomized because they're intermediate values anyway, so who cares? Right, and this entire thing can be turned into like a forward function, right? So let's actually take this entire thing and let's say float forward ZOR, right? We're gonna accept a model ZOR. We're gonna accept X, actually X1 and X2, right? We're accepting X1 and X2. Right, and in here we just like return this final thing in here, right? And we can only take these matrices, all of these matrices from M itself. So it's going to be like this, right? It's going to be A, actually A0, right? So this is A0, A1, right? So this is A0, and A1. You can already kind of see how you can just wrap this thing into a for loop, right? So if you had like several layers, like n layers, you could have done something like less than n, right? And in here you would say, okay, like I, and this one is going to be I minus 1, like a previous layer and stuff like that. You can already see a pattern emerging in here. So, right. So you can already clearly see the pattern emerging here, and this is the reason why I'm writing all of that copy-paste explicitly, so the pattern becomes as explicit and as loud as possible to sort of like make a point. Yeah, that's how you're supposed to do that. Like, this is one of the powerful things about copy-pasting. People are afraid of copy-pasting, people hate copy-pasting, but it's a very strong indication of patterns that needs to be factored out. It's sort of like a strong confirmation, like a loud signal. Yes, that's how you have to do that. And I keep confirming it. Yeah, you can see how you can abstract that away, but let's keep driving it in that direction, right? So, right, anyway. So we also have a print. It would be also kind of nice to have like a print of this thing, but whatever. Okay. Let me try to compile this entire thing just to see if it compiles. So exp, we don't have really exp, so let's include the math. Right, math. Let's include the math. So x1, okay, so we don't have to do that stuff. And okay, so what else do we have in here? A2, this one is available in here. There we go. Everything is fine. Everything is fine. So now we just got a random ZOR model, right? So we just allocated a bunch of stuff. We randomized it. Let's try to see how it works at all, right? Then we're gonna just like iterate through, like we are building a truth table, right? We're building a truth table. J equal less than 2, just to see how this entire model performs. Right, so we're gonna do forward ZOR. I provide the ZOR model, I and J, right? And that gives me something. So I might as well actually print this entire thing right away, right? So F, so it's gonna be like this. I and J, and let's see how it performs. It should perform like a garbage. Yeah, there we go. So it basically returns like, you know, the same stuff, right? So, but it works, right? So we essentially just perform a sequence of matrix multiplications and additions, and then activate them, and that's the whole passing through this entire stuff. This is the whole passing. All right, so let's try to compute the cost of this entire function. To compute the cost of this entire function, we'll need like a training data. So what I'm thinking is that what we can accept, right? So let's do cost. We accept the model, and we can accept a couple of matrices, right? So matrix training input and training output, right? So training input and training output. And essentially, training input is going to be the stuff that you are going to put in here, right? And training output is basically what you expect in here, right? So, and one of the things we want to confirm, by the way, is that the amount of rows between them is the same, right? So essentially, each row is like a training sample, right? So input and output, and it has the same amount of rows, like input and output has the same amount of rows. So we can basically now start iterating those things, right? So we can start simply iterating those things and just working with them, right? and just working with them. So less than n, and there we go. So interestingly, we could have actually accepted, we could have, yeah. What if we don't accept any stuff in here? Yeah, because that's kind of funny, but you can just like set those things directly. You can just set the input and then get the output directly, right? So this entire thing, it just sets the intermediate things and you set the input and output directly. So here then, what we do, we set up the input, right? Then we forward that XOR, and then we take the output, which is located at A2 ES in here, right? So there we go. So we supply the data for the input, we forward it, and then we took the data out of the other end. Right, so that's an interesting API. I suppose we can work with that, because why not? Right, and that thing is just like forward. Yeah, all right. So, and the thing we can do in here, right? The thing we can do in here, I want to take the current row, right? I somehow need to take the current row, and I need to set that current row to here. Yo, wait a second. This is where the idea of sub-matrices comes into play. Actually, what if okay, so I know that Ti is a bunch of rows and each row is a sample, right? So we can say that Ti is roughly something like, right, so 0, 1, and blah, 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 right? Can I have something like mat row, which accepts the number of the row and turns that specific row into a vector, into a matrix. So then I can take the input matrix from the model and say, okay, copy that row into that matrix, and it kind of abstracts away the specific sizes and stuff like that. This is actually kind of cool, isn't it? So yeah, so taking sub-matrices is actually useful. I didn't know about it, right? So, that's cool. That's actually super cool. So I think we need to implement this separation. I think these separations are going to be very, very useful. So let's go ahead and do that. So we need like a thing that takes matrix row, which is rather easy, but it's difficult to do something like matrix column, right? So you can't really take this thing as column because that already requires stride, because you need to be able to skip some of the elements within the submatrix. And that's like, yeah, so if you need mat row, you may also need mat column. And if you need mat column, you'll need to introduce a stride. So we'll probably need to introduce a stride. So that's actually, okay. It's very interesting. It's kind of cool, like developing and just like discovering these kind of things. So yeah. Okay. All right. So let's just introduce these things. Mat row, right? Mat m size t row, right? So that's the row we want to have. And mat copy, right? So this is going to be destination, and this is going to be the source, right? So we're copying two things, right? So let me find mat sum, and this is where we're gonna put all of these things in here, right? So mat row, how can we take a mat row? We can return something like this. Okay, so row and 0. And since mat at actually returns like an expression that points at actual element in here, one of the things we can do is literally take a pointer to this thing, and that's going to be the beginning of that specific row. So that means I can construct a new thing in here, right? So let's actually put it like this. This is going to be the elements, right? So this is going to be the elements. The amount of rows is going to be 1, right? So this is going to be single row. And the amount of columns is going to be the amount of columns within that specific matrix, right? And then we can just return this entire stuff, and this is the matrix that we've got. And this matrix is just sort of like a lightweight entity. This should be a very easy operation to perform. Yeah, that's cool. All right. That was rather easy. Okay, so now copy, right? To copy one matrix to another one, we need to make sure that their shapes are equal, right? So we need to do something like, and then assert destination rows equal to src rows, and the same goes to the columns. Right. And let's iterate through rows and columns in here. So this is going to be dst rows, and then size t j dst columns plus j. Right, and everything looks okay, gum. Right, so mat at dstij equal to mat at srcij. Easy peasy lemon squeezy. Easy peasy lemon squeezy. So, and yeah, so that makes it super easy to just take this specific sample and supply it in here, right? Just supply it in here, and then we can just forward ZOR, right? We're just forwarding ZOR, and we get the output as A2. And here's an interesting thing. So A2 has to be kind of like, now we need to compute the difference between the output row, which also could be a row, right? So we can say it's something like row TOI, and this is the output that we expect. Maybe we can even say something like X, like so. This is this thing, and then here we could have something like Y, which is like expected in here. Right, which expected in here. So this comparison, right? So we need to now compare Y with A2. Right, we need to compare Y with A2, which means that the amount of columns of this specific thing has to be equal to the amount of columns of this thing. So this is another condition that is very important in here, and which we probably want to put into assert here, just in case it gets violated at some point. Right, it gets violated at some point. So yeah. Right, and because of that, I think it probably makes sense to actually have this amount of columns as a separate variable in here. Maybe I'm gonna actually, well, it's already, we already have m. God damn it, we already have m. Let's actually call this x, right? Because it's ZOR, right? So this is, god damn it. Okay, whatever. I can maybe call it q. So all of the variables are already taken, all of the names, all of the one variable names are already taken, and that's why you should not use one letter names. That's the actual reason, because you run away of them very quickly. Right, so this is going to be something like this, and what we need to do now, we need to just compute the differences between them, right? So essentially, so the actual output A2, right, the actual output at row 0 but column j, right, so row 0 but column j, minus whatever we expected in y, right, whatever we expected in y in here. And that's sort of the difference, right, that's sort of the difference. And we need to take the square of that difference and add it to the cost function, right? So we need to add that stuff to the cost function, and the cost function here is going to be initialized with 0. So as you can see, we're just like, you know, populating the entire cost function. Where is it? Okay, I lost it. Okay, and after we populated like the sum of all of the samples, we need to divide it by n, by the amount of samples, and that gives us the cost. Right? That literally gives us the cost. So could be kind of interesting. So what effectively this is a square distance of this stuff, right, between these vectors. Can we do something about that? But maybe not. Anyway, so now what we can do, we can just print the cost of this model, right? So let's actually print the cost. So cost, what does accept cost? And yeah, so we have to provide the model, and we have to provide TI and TO, right? So, but we don't have them, right? We don't have them. So let's define, right? So let's define the training data, right? So maybe we can define it like TI, right? Which is going to be just this, right? So this is going to be just this. Yeah, so 0, 0. I would like to have like all of the training and expected data in here. I feel like I want to have that like this, right? And then we're gonna swap it around. And since it's XOR, like here we have to have a 0. So this is the initial training data. And one of the things I want to be able to do, right? I want to be able to take sub canvases in here, right? So not sub canvases, but sub matrices, right? Sub matrices. So I want to be able to take this as a sub matrix, and I want to be able to take this as a sub matrix as well. But it's not impossible column wise because we don't have a stride. Maybe one of the things we have to introduce in here, we literally have to introduce a stride, right? Size t stride. Okay. But that requires setting up that stride every time we are constructing anything, right? So we need to find all the places where we, for example, set the rows. Okay, so that's cool. When we're allocating something, we can always set the stride to the amount of the columns, right? So the actual width. Is there any other places? Okay, so this one is interesting. All right. So when I take a row, right, I think I have to reproduce the same stride as this original stride of the matrix, right? Because here I effectively take a sub-matrix anyway, right? If I had a certain stride, yeah, that makes sense, right? So, though, since it's a single row anyway, stride is not particularly needed, right? Stride is not particularly needed. So is there any places where we set the rows? Yeah, so that's the only place, so yeah, that's cool. And essentially, when we do add, instead of doing columns, we have to set the stride, right? So I'm really curious, like, I hope we don't try to access ES directly, and in the places where we access ES directly, we do take stride into account. So here we do take stride into account, so everything seems to be fine. Here we also do take stride. Okay, so all of the access to the elements here is actually abstracted away, and I'm super happy about that. So I'm super happy about that. Cool. So, and I wonder, like, now we need to do, you know, a sub matrix. So this is the row, right? So can we do something like mad sub, right? Mad m size t. How can we take that? I don't really know how to come up with this thing in here, but I think I can just do that manually. I think. Right, let's just define it manually. I think it's gonna be easy. Right, we need one way to decide the amount of samples in here, right? So we can say that the n is actually size of this thing divided by the size of this thing, right? Actually TD0, right? So that gives us the amount of elements in here, and we have to divide it by 3, and that gives us the amount of samples, and that's very important because this is the amount of rows, right? Then I can take the TI, right? And here I'm going to say, okay, the amount of rows is the n, right? The amount of columns, though, is 2. Stride is 3. Stride is 3. So maybe we can even have this as a stride, so we can reuse it like that. So this is going to be the stride. So this is a stride, and the elements start at TD, right? So the elements start at TD. So, and then I'm going to do TO, right? So rows is n, columns is 2, right? Stride is the same, but we start at a different place. We actually start at 0, 1, 2, right? I suppose we start at 2, or maybe we can even do something like TD plus 2. So that's it. We can even confirm that everything's fine. So let's do matrix print print TI. So we print TI and TO, and let's see if it actually successfully split this data into two separate matrices. So the first matrix has to be this, the second matrix has to be this. Right, so that's what we're trying to do in here. Let's see if it's going to work. Doesn't really compile, which is fine. Conflicting types, mat row, why are they conflicting? Oh, okay. Why was it okay before? That's weird. I don't know why. I don't know what happened. Maybe it never worked. Closer. All right. So a forward implicit declaration, that's very interesting. So why is it implicit? Oh, this is because it's defined down there. So we have to do that in a different order. We have to do that in a different order. And boom. Did that work? I don't think so. I think that didn't work because we have two columns in here, and I think I did an oopsie doopsie and potentially a stupid fucky wacky. Right, and I literally put columns 2 in here, but I have to have 1, and there we go. I think I fixed the problem. So let's actually compare this kind of shit. Yep. So the actual data here looks like this, right? So it's continuous in memory, but our structure for matrices allows us to carve this as a separate matrix and this as a separate matrix without doing any copies or anything like that. So we have some data in the memory, and matrix data structure, right? This specific matrix data structure, let's actually find it, is just a view on that continuous data of floats, right? And we can basically represent them however we want, right? So I just basically carve out this as inputs and this as outputs, but I can actually store that like continuously in memory if I want to. So I think this is a very interesting approach. It's kind of like similar to canvases in OFC. That's actually very interesting, like a flexible way of working with that. So yeah, so you have all of the parameters of the neural networks like continuous in the memory, and then you just like take sub views for specific layers and stuff like that. Furthermore, the entire data for this neural network could have been just a continuous array of floats. We can just pre-allocate continuous array of floats for all of that. And for these specific matrices, we can just like specify sub like views on that specific memory. And you know why this is cool? Because it will allow to just dump the current neural net state into the hard drive, and that's it, without creating any special formats or anything like that. You just like dump it into the hard drive and that's it, and then you load it up again. Very easily, because it's a continuous array of floats anyway. It's just like how you view that array. That's what makes the topology and stuff like that. But you also need to store information about how to do topology, and like at least the sizes of the layers and stuff like that to pre-allocate all of that. And it's actually kind of cool. Well, you probably don't want to save the intermediate values in here, but you can actually have this intermediate values like A1, A2, A3, right? So in a separate continuous space that you don't dump, right? So you have a special continuous space of parameters that you do dump, but you have a separate thing for these intermediate things, and they don't really intersect too much. Yeah, this is actually kind of cool. Yo, this gives me so many. This is so cool. Why am I so fascinated by such a simple thing? It's just like, yeah. And because like this is cool because it gives you serialization automatically. It gives you serialization automatically. The beauty of the matrix forward propagation is that you can use matrix instead of a vector as the input, and you'll get a vector of outputs if you fix the adding of the bias. Well, yeah, that's literally what we're doing here, right? So that's basically forwarding. So multiplication, bias, activation, multiplication, bias, activation. We haven't abstracted away the amount of layers yet, but we're getting there. Okay, so let me see what we've got. Yeah, so everything seems to be working. So now I can just like pass Ti and To into the cost function, right? So I was doing that specifically because I wanted to compute the cost function, right? So maybe I want to disable the final verification of the model, right? The final verification, and let's see how it's going to go. So this is the cost function. That's cool. Why don't you store only one activation layer and use it as an accumulator? Because it has to be different shapes, right? Because the activation layer changes its shape depending on the specific layer, right? So because once you pass the input through this layer, you have activation of, like, you have two activations. Once you pass two activations through that layer, you have one activation. If you have more complicated things, so as you can see, this thing sort of varies and stuff like that, but you can probably have a single continuous buffer that should vary, right? That should vary, right? But I don't want to do that yet, because actually having these buffers being independent things is very useful for backpropagation, but I don't want to go into that yet, right? Even though they're intermediate and for activation, they're actually very useful when you start coding backpropagation, because you can store intermediate things in there as well, right? You can use them not only for just activation, but you can go with them in a different order. So I'll demonstrate that on the next streams, right? So because I don't want to do any backpropagation right now. Now, so we've got the cost, right? So the time has come to implement like finite difference for this entire cost, right? So let's find how we can do that. Finite difference. So the thing about finite difference is that it kind of returns a gradient in air quotes, because it's not really a gradient, right? So it's finite difference. Because of that, we need to accept two things in here. So accept the model first, and then we accept the gradient that we're going to have in here, and also an epsilon by which we wiggle the parameters in here. Right? So by which we wiggle. And what we need to do in here, we need to do copy paste again, right? So we need to do some copy paste again. So this is going to be a saved parameter. All right, let's iterate through the first weights, right? So we're going to be basically iterating through all of the parameters of a neural network, and we're going to be wiggling them and computing the cost of them. So to actually have the original cost, let's do cost, then the model, and TI-TO, which we'll probably want to pass in here as well. TI-TO. There we go. So let's iterate through the W1 rows, right? So we're iterating through this entire thing. So we'll still need to do a couple of like a copy paste and stuff like that. Right, so it's gonna be J. So let's save the current parameter matrix at MW1 I and J. So we saved this entire thing. Then we are wiggling it by that specific epsilon, right? And then we compute the cost after modifying this entire thing and subtract the original cost and divide it by that little wiggle. And we set it to the gradient, right? So it's a very dumb way of doing that, I know, but I do that intentionally, right, for the sake of simplicity, right? So we're not doing backpropagation yet. And then I'm restoring the original value saved in there, right? Okay, so that iterates through all of the weights of the first matrix, and we kind of want to do a similar thing for the biases, right? So in here we'll have to do W1, B1, similar thing, right? So, and now we want to do this for W2, right? We want to do that for W2. Let's replace W1, W2, boom, and guess what? We want to do that for B2, right? B2, B2. Cool. I know what I'm doing. I'm a professional software developer. Trust me, I know what I'm doing, right? So, as already said, copy pasting is useful because it's a strong indication of places that needs to be factored out, right? So no, I know, it's beautiful. Anyway, so okay, so we have a finite difference, and yeah, now what we need to do, we need to sort of pre-allocate a similar thing for this thing, right? So maybe we can have something like, so we have Zor, right? We can create Zor alloc, right? And it's not going to accept anything. What it's going to do is just this, right? And just return this entire thing so we can reuse it at least 2 times, right? So this is the original model, Zor alloc, and this is going to be a gradient, right? Gradient, Zor alloc. So we don't really need to, initialize the gradient, it doesn't really matter. And what we want to do, we want to do finite difference. In the finite difference, we provide the model, the gradient, the epsilon, which will we go. I usually like to pick something like 1/10, and the input-output data, right? So that's what we got. So after that, we need to basically apply that gradient, right? So we need to apply that gradient with a certain learning rate. So let's create a function learn, which accepts the model and the gradient, right? And the rate with which it is learning, right? So basically the rate. We're gonna do another naughty thing in here, like so, where we take the parameter and we subtract the gradient parameter multiplied by the learning rate, like so. It's a little bit smaller, but still kind of naughty. So we don't really need this stuff anymore. We don't need this stuff anymore. And here we have B1. This one is W2. B2. So that's how we apply that. All right. That's how we learn it. I can say maybe it could be called Zor learn. Right. So we've got the original model. We computed its cost. Then we found the finite difference gradient, so to speak. Then we apply the gradient, right? So learn mg with a certain rate. I found that the rate of the same side as epsilon kind of works well. And I want to now print, the second cost after the modification. Zor learn, sure. I mean, the compilation will tell me. Okay, so saved, yeah. That's why you should not copy-paste, chat. Never copy-paste, because you copy-paste errors. Right. All right. Did that reduce the cost function? I think it did. I think it kind of did reduce the cost function. I'm reporting you to Uncle Bob with all this naughtiness. I'll complain to Casey. So he will protect me from Uncle Bob. Anyway, so yeah, we can maybe increase the learning rate, but we'll see. So, and what that means is that we can. We've got somebody throwing money at me without knowing that I don't get any of that. For some reason, I can't see money. Money where? Twitch. This page is dead. Yeah. This page is dead. I wonder. Oh, I see. Okay, nice. I have to reload everything now. You thought machine learning is hard. You know what's harder? Web applications. It's the most difficult computer science problem on planet Earth. So thank you so much, Max Nothing, for 1,000 bits. Thank you for gifting money to Jeffrey Bezos, because I don't get any of that, but thank you. Tem Uzenlar, thank you so much for 5 community gifted subs. Thank you. Alrighty. Cool. So what do we have? Yes. So that means we can just repeat this process, right? We can repeat this stuff several times and drive the entire cost maybe down? Maybe? I don't know. Let's repeat that 10 times. Right. Let's repeat that 10 times. Is it going to work? It's kind of going down, not gonna lie. We can probably also print the current iteration just to see how well it goes, and let's try to do that 1,000 of times. Is it going to... At least it went below 25, which is already a good indication, right? So if you usually if you don't have enough neurons, Zor will just stay at 25, I think. Right, it will just stay at 25. So that's actually a good indication that we're doing something right. Okay, so I'm gonna use the different terminal because Emacs is kind of slow as a terminal. Right, so, and let's do that maybe 10,000 times, right, 10,000 times. This is, okay. All right, it just went somewhere. Okay, and now I want to enable verification, if you know what I mean. So essentially, just you iterate through all of like truth table, build the truth table with that specific thing. Right. So just build the truth table. And does it look like Zor? Yeah. So this thing is supposed to be 0. It's below 0.5. This thing is above 0.5. That means it's 1. Above, below. So if we just like train it a little bit more, it will be closer to 0. This one's been close to 1, and it kind of converges, right? So it goes somewhere. So we basically migrated this model to matrices, right? And it still works, right? But now it is more kind of like flexible. We can add more neurons, for instance, right? So, but to add more neurons, right, we'll have to change these things, right? So, and the main problem here is keeping track of all of the sizes and stuff like that, and it's kind of painful to do that, if you know what I mean. It's just like kind of painful. So it would be nice, right, to actually go one step further in a level of abstraction, right, and introduce the notion of the neural network as a collection of matrices, right? So right now, Zor is basically a fixed collection of matrices. But what if we want to build any kind of sort of like neural networks with any collection of matrices? Let's go ahead and try to abstract all of that away. So we can say that this is a neural network, like abstract neural network. Right, and here we have array of weights matrices and array of bias matrices, right? So we need to kind of know how many of these things we have, like how many layers we have. So let's have something like count, right? So this is going to be the count. And then here we have weights, biases, right? And we also need to have inputs, right? We also need to have inputs, but in case of inputs, we have to have one additional thing in here for like the initial input. So maybe this specific array is going to be one element bigger than these two, or something like that, right? So because I don't really know how to organize it better, we can say the amount of activations is count plus 1, right? So some sort of a node, right, to remember. So this is count, but this thing specifically is count plus 1 because like you need an additional thing in here, right? And there you go. So this is our neural network, right? This is our neural network. And we want to be able to allocate neural networks as easily as we do with matrices, right? So we would have want to have something like an alloc, and here we want to specify the the architecture of this entire thing, right? The architecture of this entire thing. How can we do all of that? That's a very interesting question. So first of all, we need to supply count, like how many of these things we have, right? We need to supply count. Then we need to know the sizes of this entire stuff, right? So we know that the input is 2, like, right, there's 2 input neurons, then there's 2 hidden and 1 output. It would be kind of nice if I could just allocate new neural network by doing stuff like this. Right, I could just say something, okay, right, so this is architecture of the neural network. Go and configure and allocate matrices according to this specific architecture. Right. So that would be kind of cool. But we are talking about C. We're talking about C. We could try to do some variadic shit, right? So we could try to do some variadic shit. But unfortunately, it's very error prone. And I don't really want to do that. So what I'm thinking is that maybe we could accept count and array of layers, right? Something like that. But this thing right, this thing also returns you the input. So you actually have two layers in here, but one input layer. Right, so this one is complicated. So if there's three things in here, there's actually two weights and biases. So maybe we could accept, okay, so this is how many inputs we provide, and then the count of how many layers, and then the layers themselves, or something like that, right? Maybe. I still haven't decided on how exactly I want to do that, but yeah. So there's the inputs, and the inputs will define the, like, basically an n as 0, right? An n as 0. So we can do something like this. And here, that means how we're going to do that. So it accepts two parameters. Then we could have additional thing in here, which is basically layers. And layers are 2 and output 1. And then you can have something like count, size, well, you have to do some more, yes. Size of layers divided by size of layers, 0. Right, so 2 input parameters, counts, and layers. Right, so with C, it's kind of difficult to specify all of that. But it would be kind of nice if we could just do it like this. Right. But I mean, it has to be like this because it's the count in here. So the count is not equal to the count and n because it's +1. So maybe I can say something like, yeah, it's not layers, but let's say this is a description, right? So this is description, or maybe architecture, right? Architecture, and then architecture count, right? So that's what we have in here, and it contains like everything that you may need, right? Everything that you may need. Right, so that looks like a reasonable thing to have, right? That looks like a reasonable thing to have. On top of that, quite often I've seen some C code define this kind of macro, right? Define this kind of macro where it takes sizes, which is basically axis, like so. So then you can quite easily just do shit like this, which makes this entire stuff even simpler, right? So if you want to allocate it like that, and here you specify the architecture. We can even say arch. Okay, so I think I came up with a good API, right? How do you guys like this API? Right, you have an architecture of the neural network. So this 2 inputs, 2 hidden and 1 output, and you sort of pass this architecture like that. With this macro, it makes it a little bit easier, and it just like allocates enough matrices and configures the sizes and stuff like that. Right. So that's actually kind of cool. Yeah. So, and it makes it super easy. Okay, I see that this neural network performs poorly, right? So I can add another like layer in here, and it will just automatically do that. Like reallocate, reconfigure, and it will just allow passing through this entire network very easily. And then no, it's overfitting. It's too many parameters. Let's actually remove that. Yeah, that's cool. Yeah, let's actually try to implement that. So this is a very good API, I think. Okay, so and let's transform this entire stuff into that. So this is going to be NN, right? So the count here, right? So the count is actually the amount of inner layers, right? But the arch count includes the input layers. So because of that arch count, right, -1 equal count, right? So that's how it works essentially. Okay, so what that means, we need to pre-allocate arrays of matrices in here, right? So we need to pre-allocate arrays of matrices. So we need to allocate WS, which is going to be size of WS M and then WS, right? I'm allocating an array of matrices. Malloc multiplied by an n count, right? So that's what we do. So this is an n count. We might as well assert saying that this thing should not be equal to null, right? Next thing is going to be BS, right? I'm allocating BS in here, and that thing should also not be equal to null. And the last thing I'm allocating in here is actually AS, but count here is +1, right? Or we could have said arch count -1, but I don't know. So it depends on what kind of intentions I have in here. Okay, so we pre-allocated arrays of those things. And then assert. Oh yeah, so we actually have an assert, but that means I have to move this entire stuff to NNH. I want to do that after I finished implementing all of that. But I mean, it probably makes sense to actually start using the frameworks things as soon as possible. Yeah, thank you so much. Let's do assert, and there we go. So we pre-allocated all of these things. And we need to start configuring this entire stuff. So let's actually start with the first input layer, right? So the first input layer is very important. Right, it is very important, and we need to do mat.alloc, right? Mat.alloc, and the input is just a vector, right? It's just a vector with a single row, right? With a single row 1, but the amount of columns in there is actually arch 0, which also implies that arch count assert can never be equal to 0, right? It should be at least 1, otherwise it kind of doesn't make any sense, right? Kind of doesn't make any sense. So this is the first allocation that we have. So, and then we need to start allocating the rest of the layers, so to speak, right? The rest of the layers. So let's do the iteration and then count, right? ++i. So in here, we're going to be allocating and then ws, and then ws is going to be I, and what's going to be the size of the entire thing. So we have the previous layer, and its amount of columns should be the amount of rows. Its amount of columns should be the amount of rows. So that means, and then as I columns is the rows for this thing, but in terms of columns, it is the architecture of this thing in here. So that means we have to do arch, arch, but already +1 because we already used up the 0. Which actually brings us to a very interesting question. Could we just do something like 1 and arch count? Okay, so, and that means this thing has to be like -1. This one is -1 because we kind of take the previous one, and arch is this. Is that a good idea generally? I don't know, we'll see, So there's that. Then we need to allocate the biases, right? We need to allocate the biases, right? So this is alloc, and the biases need to have essentially the same architecture, well, I mean, the same shape as the multiplication of activation, the previous activation, and the weights, right? So essentially, yeah, it needs to have the same shape as this thing. So which means that it's probably going to have one row, but how many columns? I think it's going to be like literally the same amount of columns as here. Okay, so and what we do is the next activation in here, right? The next activation in here, which again is going to be 1. Oh, since there have to be, okay, I see. So they literally are the same as the activation in here. So I think that should work. I think so. A bit complicated, but I guess that's fine. All right. I guess that's fine. All right. All right. I would like to test that thing already somehow. But unfortunately, if I try to compile this entire stuff, it's going to crash because I got rid of the XOR alloc. Right, so I got rid of the XOR alloc. I should have not done that, right? So, because All right, it doesn't allow me to migrate this entire thing easily. So I have an idea. I'm gonna move this entire stuff inside of the framework, right? Inside of the framework. So I need to find nn.h, nn.h, and let me find it in here. So this is gonna be that. This is very abstract macro, so we're gonna put it in here. So because I want to have something that is basically abstract up top, then matrix related, and then neural network related, right? I think that would make sense. So I'm going to take this thing, and this is allocation, and then the implementation of this entire stuff is going to be down there. All right. So, and now I want to do Control Z, right? So because I want to restore the original code because I want it to be compilable, right? Because I want to gradually migrate towards a new architecture. And by just jumping and removing everything that already works, it's not gonna go really well, if you know what I mean, right? So let's go back. So yeah, there we go. So that looks all right. So now if I try to build this entire thing, it seems to be working. So here it returns m, it should return nm. Okay, cool, nice. So should be working now. So what I want to do, I want to be able to also print neural networks similarly to how I print matrices. In fact, I want to have a similar API for neural networks as for matrices. Like I literally want to be able to do and then print where I just accept neural network, and I probably will need to have some sort of a name for a neural network, so it makes sense to put it in here, so that then later I could have just a single macro and then print, right, that just does everything for me, like so. Right, we want to be able to do this kind of stuff, if you know what I mean. All right, so let's go ahead and implement that. This one's going to be really interesting. So printf name new line, and then let's close this thing. So how are we going to be doing all that? I suppose we just need to iterate through the weights and biases, and that's it, right? So, and then count, not const, count, I said, and then count, and we want to do mat, mat print. This one is interesting though. Yeah, I suppose we want to do mat print, like a big one. But since it's a name, yeah, I have an idea how we can do that. Because I want to have specific name, like all right, so let's have mat ws, right? So mat ws, and then ws, and then bs, like so. So then later I can do wsi and then bsi, and the problem here is that this thing, it's not gonna work well because it's literally gonna give you this as an expression. Okay, so let's just try that and you will see what I mean in here, right? So, and because of that it doesn't really matter, so we can just do and then like so, right? So let's just do and then like so. Okay, so this is name, this has to be a name. Yeah, it's going to include the I, right, you're right, it's going to include I, and that's the problem, right? You get it right. Okay, so let's do size t arc, all right, and we want to have 2, 2, 1, right, and then let's allocate the neural network, right, let's just allocate it. So this is the arch, array length of arch, and then print, and then Okay, so let's try to do that, and let's try to run this entire thing. And what do we get? Yeah, so that's the problem. So I can see two problems in here, right? I can see two problems. First of all, I literally want to have 0, 1, and so on and so forth. So that creates some sort of a like challenge. Second of all, I would like this thing to actually be indented a little bit, right? If you know what I mean. Like it would be nice if it would just like indent it, because I can't see shit in this mist, so I don't think it's particularly useful. So what I'm thinking is that maybe we could extend the print a little bit, right? So first of all, we're gonna use this print directly. For the name, I'm gonna just put WS and BS in here. And we probably want to add another thing that adds the padding, right? So some sort of a padding. Let's say it's going to be four things in here, right? And we can say size T padding. And by default, for this macro, padding is going to be 0. We're not going to add any padding, so it's going to be hidden away, right? So in this one, size T padding, and we just add this padding in front of all of these things, right? So size TI 0 padding. So maybe there is a way to do that with like printf formatting things. I think there it's actually better to do it with printf formatting things. Right, we can do, I think you do it like that, and then you say okay, padding and just nothing, or I don't quite remember, right? So but I also remember that you have to do it like that. All right, and yeah, it's gonna be S. So we'll see. Okay, so printf-c pad left pad with spaces. I remember there was a trick to do that. I remember there was a trick, but I don't quite remember. Left pad printf spaces blah blah blah. Yeah. Okay. Oh yeah, I was actually kind of right. So yeah, so this is the star, because I kind of vaguely remember. Right, I kind of vaguely remember. But then padding goes, yeah, so then this is, so essentially it makes the string of a certain size, of the size of the padding, right? But then the string is empty, so that's why it's gonna just create this amount of like, what is it called? This amount of spaces, so to speak. All right, so let's put this stuff in here, and so it's kind of weird. It's the weird way of doing this kind of stuff, but it is what it is, and it isn't what it isn't. Is it not? I think it is. The missile knows where it is because it knows where it isn't by subtracting the deviation. Okay. So let's try to recompile this into a thing. Yo, what the fuck? Almost, it actually added more spaces in here. So I think I need to address that actually. So I think we only need to add this sort of padding at the beginning of the stuff. Right, and for the rest of the stuff, don't even care, bruv. Bruv, don't even care. So we're gonna do build and then NN. Look at that beautiful neural network. Look at that beauty. Doesn't look cool? I think it looks kind of cool, and it actually precisely allocated like the things that we wanted, right? So because the this thing has to be 2 by 2, and then bias is 1 by 2, and then the weights here 2 by 1, and then the final thing is 1. So that's perfect. Right, so that's pretty progress, but this is not enough, because what I want you to have in here is like the numbers of those things, like the actual numbers. The question is, how can we achieve that? We can probably achieve that by sprintf, probably, right? So we can allocate some sort of like an inner buffer, right? So 256, and we can just do snprintf ws, and we can put this thing like so. snprintf accepts the buffer and size of the buffer, right? And it's supposed to return, well, it doesn't really return anything, but effectively what you can do, you can just then put this buffer in here, and then you can do bs in here and put this buffer in here. right? So we just allocate a little bit of memory on the stack, we render some names into that memory, and it should basically create a pretty cool shit where you have WS0, BS0, WS1, BS1. And all of that is with pure C. How about that? How about fucking that? So, isn't it poggers? I think it's pretty freaking poggers. So, and if you want to have more of these things, right? So essentially, let's say, what if I want to have another layer of 2? And I'm gonna just add it in here. So is it going to work? All right. So yeah, that created another one thing here. What if I want this inner layer to be like 10? So it's gonna create like a matrix of 10 by 10, literally. I'm not even joking. Look at that. Actually, no, not really 10 by 10, but it depends on if you're gonna actually have 2 of 10. Yeah, this is when it's gonna create. Yeah. So this is basically representation of this neural network in terms of matrices. And look how flexible it is, right? So we can just like specify the architecture, and there you go. It's pretty cool, right? So, but we don't really need that powerful of a thing, right? So what if we wanted to do the classical MNIST thingy, right, with the 3 blue 1 brown architecture. 3 blue 1 brown, right, did architecture where MNIST is 28 by 28, right? So this is the input. Then he had 16 inner layers and another 16 inner layers, and the output layer was from 0 to 9. So this is the architecture of the neural network that the 3 blue 1 brown used for his neural network series, right? So how would it look like? Right. It's fucking enormous, actually, if you think. Well, I mean, it's not really enormous, but yeah. So that's a lot of different parameters in here. Yeah, that's it. Imagine training something like this. But though, it's kind of weird. All right, there's one. Oh yeah, okay, so that's fine. So there's three layers in here. Right, so and all of that is parameters. So as far as I know, it basically has 13,000 parameters. Right, so this entire thing is 13,000 parameters. Right, so we're not going to be doing that. This is going to be 2 inputs, 2 inner layer, and 1 output, and that's it. And this is a very small and neat thing. So another thing we need to be able to do, we need to be able to randomize this entire stuff, right? I want to be able to do, and then rand, similarly to how we do that with the matrices, right? I want to be able to just say, okay, randomize this entire neural network. Randomize it. So we have already mat rand, as you can see, right? I'm going to copy paste this thing here, and it's going to be NN neural network. So, and what we're going to do, right, so we're going to iterate through all the layers, right, so these are just the layers, NNWSI, randomize this matrix, and randomize this matrix. There you go, we just randomized this entire scheisse. We also have to provide low and high. This is low, this is high, boom, no, almost. So we have to provide this thing here, so let's say 0 and 1. Okay, so this is a random neural network. So we probably want to randomize the seed, gut seed. Okay, cool. So that's nice. Now we need to be able to forward the neural network, right? So here, as you can see, we hard coded these 2 iterations. Let's actually go ahead and simply, you know, abstract this thing away, right? So we can say and then forward, right? And then forward, we're gonna accept the neural network, right? And we're gonna start iterating through its layers, right? So this is gonna be size t 0 and then count. And this is what we're gonna be doing in here, right? So essentially we take the first activation layer, which is the input actually, right? And we're multiplying this thing with the first weights matrix, right? So it actually has to be I. And we're doing that into the next activation layer, right? We're doing that into the next activation layer, like so. Yes. Into the next activation layer. Then, to the next activation layer, we're adding the current biases, right? And then we're activating, well, it has to be some. We're activating that next layer. And since the amount of activation matrices is n count plus 1, this is not going to overflow at the end. You know what I mean, right? And that's it, right? So this replaces this entire thing. So basically, it's the same thing, but in a loop, right? And it accommodates any amount of layers, right? It accommodates any amount of layers as you want. So this is how we're going to be doing forwarding. So as you can see, we're rising the level of abstraction in here. We keep rising the level of abstraction. So it becomes more and more abstract, which is freaking poggers, isn't it? I think it's pretty freaking poggers. Okay, so we can try to forward some shit into this neural network, but I'm not sure if it's going to give anything meaningful. Right, if it's going to give anything meaningful. So let's take MyPaint, right? So we already kind of prepared the input data, right? So let's actually take this entire stuff, all right? Move all of that stuff in here. And this is where we're going to allocate the neural network. So this is the input data, right? So this is the input data, this is the output. And you know what I want to do? I want to take the mat_row ti 0, right? So let's take a look at it. MyPaint. Yeah. MyPaint doesn't work. Oh yeah, because this has to be and then. And then just a second, going through the compilation errors. That's why you have to program in Python. You don't have to worry about compilation errors. There we go. So this is the first row. Look at that. Like it literally gives you the expression. This is why I used that thingy. MyPaint, which stringifies, because it literally stringifies your expression and it gives you like information what exactly you're printing. Look at that. This is so cool, right? It's a very useful feature. And this is C. This is pure C. Right, anyway. So let's actually find something, right? So if we take a different row, yeah, this is a different row, right? So let's copy that row, right? Mat copy into the input layer of the neural network. And the input layer is the first one, right? So this is the 0, this is the input layer, right? Would be kind of interesting to maybe have something like, and then input, and also, and then output. Wait a second, that's actually super cool. I want to do that. Yeah, define, and then input, and then a s 0 and output and then count. It's just like semantically nice, you know what I mean? Right. So essentially I take the first row from the training data and copying it into the input of the neural network. Then I forward the neural network and then I'm just printing the output of that neural network. Yo, what the fuck? This is so nice. I mean, that's a useful framework, like syntactically even. Like even syntactically. Right, just look at that. And this is the output, right? This is the output. Maybe we can just take a look at that, right? So this is basically row, right? MyPaint row. So we're going to print the input, forward it, and this is the output, right? So we have the input in here, and this is the output. We can go through other things, right? If I do 2, right? So this is another one, and 3. Yeah, it just makes it easier to debug and, you know, do some other stuff. That's pretty cool. What the fuck? Is this like starting to turn into like an actual ML framework? What the fuck? Yo. Anyway, so okay, that's pretty cool. And one of the things we probably want to do is essentially just maybe verify, right? So maybe turn this into a verification, right? Maybe turn this into verification, but yeah, whatever. So we need to have a finite difference for that specific neural network. Right, we need to have a finite difference. The way we implement finite difference here is like this, right? But we need to do that for the neural network. Okay, so let me see how we can do that. So the signature is this, and then a loop. So this one, and then finite diff. So it would be kind of nice to have like a shorter name, because we have, and then rand forward, I don't know. Okay, so let's use for finite diff. Yeah, so let's put diff anyway. And then M, and then G, right? So epsilon and the input output. Though, yeah, so I think that would be nice. So this is more of a like in, out, right? So this is in, out, but this is not necessarily in, out. It's, yeah, it's specifically the training set, right? So that makes sense, right? Specifically the training set. Okay. So let me find this thing. Finite if. Finite diff. So essentially, we want to be able to compute the cost in here, which means that we probably want to start with computing the cost, right? So finite diff, let's introduce something, and then cost, which accepts this thing, right? The neural network itself, and you know, the inputs and the outputs, right? The inputs and the outputs, right? So this has to be the cost, so this is going to be, and then G epsilon ti to. So in the cost is essentially, right? So I can probably steal some of this stuff in here. Yeah, there we go. So it's quite important that ti and to has the same amount of rows and columns, right? The same amount of rows and columns. Right, then we start with initializing this entire thing and iterating through all of the samples, right? Iterating through all of the samples. Then we're taking the rows of the samples, right? Essentially, this is the expected input, and this is the expected output, right? Expected input and expected output. Then we're copying the input into the input of the neural network, but this is kind of interesting. So we can do it with our network framework. We can do it like that: mat copy, neural network, input, and then x. There we go. So this is the expected input. We're copying it into the input of the neural network. Right, so that's how we're going to do that. After that, we are forwarding the neural network. So at an output, we have the final output. Right, so that's what we have here. And yeah, essentially, we want to make sure. So we have a bunch of actually asserts in here. Oh yeah, I see. Yeah, so here, this is the output layer, right? So we have to do an output of the neural network has the same amount of columns as the columns for the output training samples, right? So that's basically what we have in here. So that's quite important, actually. And I can copy it in here, and we start iterating this stuff. And we are finding the difference. So this is the NN output, right? Yeah, this is perfect, right? And then we just return this cost divided by n. Perfect. So that allows us to just take a look at the current cost of our neural network, right? So what's the current cost? The usual thing that I do in here. What's the current cost? And then cost neural network TITO. All right. So what do we have? So the cost is 28. Makes sense. Okay, that's cool. Next thing, finite difference. For the finite difference, we have to do the usual thing of, like, you know, just wiggling things around, right? So let's just do float saved. float saved, iterate through all of the layers, right? Iterating through all of the layers within the layer, and then WSI, we're iterating through the rows, right? So this is size tj, j less than rows plus plus j, and then within this thing we're iterating through all the columns, right? So this thing becomes very abstract, very quick. So this is k, actually this is I, excuse me, and the single parameter is met at and then WSI JK, right? So this is like a you know, 3 nested loops, right? So we need to save this entire thing, then I'm wiggling this thing around, right, and then computing the cost of this neural network, right, the cost of this neural network, and subtract the cost that I computed before. So we have to do something like it accepts the training parameters, right? So it's going to be ti to, so the cost here, and then cost, and then ti to, right? So there's that, and then we divide by the size of that wiggle, and we essentially save it to the gradient. We essentially save it to the gradient. There we go. And then we need to restore the saved value. We need to restore the saved value. This is saved. So it's kind of similar to what we were doing in here when we were copy pasting, but now we managed to compress this entire thing because we can iterate through all of the layers. But we still need to copy paste this thing a little bit for the biases specifically, right? And this is, by the way, what would have been super useful if all of the parameters were in a continuous space, so we could compress everything into a single continuous array and just wiggle on the elements of the array, and it will just work automatically. So it would be kind of cool to have a way to just iterate all of the like known parameters. So I'll think about that actually. So AWS, BS, oh, rows, nice one. Okay, so this is WS, and that's basically it, I think. Yeah. So we're just like wiggled things around, and we populated this thing. Populated this thing. So all right. So looks okay. Let me try to compile this entire thing. So let's go through the compilation errors. And this is what we've got. We've got the gradient. The thing is, we still need a thing that applies that gradient somehow, right? Okay, so here is the thing itself, right? Let's allocate the gradient. Luckily, it's super easy. We just call this thing twice, so this is the second gradient in here. Then we compute the cost. Okay, so we've seen the cost. Let's do nn finite difference, and then j epsilon. Do we have the epsilon anywhere defined? Yeah, here it is. So let's actually bring that thing in here. It's going to be useful. TITO. So that gives us the gradient, which we want to apply, right? So let's say learn, and then j with the rate, right? With a certain learning rate. So and then finite difference, and then learn, and then has to be n in my opinion. And then G and learning rate. There we go. Okay, so here we kind of have to do the same thing. I know. And it's just like easier, right? So and then rate multiplied by the gradient, and that's it. I wonder if we can, like, the only way we can compress that even further, right, is only if we were able to iterate the parameters of the neural network in a continuous space, right? Because that already is like really well compressed in my opinion, right? It's already really well compressed. So it would be better to just have like one single for in here. But I mean, once we start doing backpropagation, all of that will go away because it's a very stupid way of computing gradient anyway, right? So it's very stupid anyway. WSBS. Okay, so I hope I didn't make any oopsie doopsie and a potential fucky wacky. Right. Okay, so let me recompile this entire stuff. It doesn't really compile because why? Oh, it's already taken. God damn it. So yeah, but maybe we can simply, yeah, we can probably get rid of all of that already. So I don't think any of that Zor stuff is needed anymore. All right, because we're almost done. We're almost done. There we go. Okay, if I try to run this entire thing, let's see, does that reduce the cost function? It freaking does, which means I can run that in the loop. Right, I can run that in a loop for size 0, thousand of times, right, 1,000 of times, and there we go. And it kind of does it work? But it's, yeah, sometimes it gets stuck. All right, so I think I need to do that in here, right? So 1,000 is just like not enough in my opinion, right? So at least for the way we do that, right? For the way we do that, 1,000 is not enough, but it's usually rarely enough. Okay, I hope I didn't make any stupid freaking mistakes, man. So rate is as usual. Yeah, there we go, it goes down. Okay, so we didn't make any stupid mistakes. Yo. And it went relatively well. So let's try to verify this entire thing. The way we verify that, right, the way we verify that is by iterating 2 by 2, right? So this is a 2 by 2, J, and what we have to do in here is we need to take the input of the neural network, right? And it's a matrix, so it's a row, right? So that means row is going to be 0, but the element, the column 0 is going to be I, and the column Y, you know, this one is going to be J, right? So this is the input, and the output, all right, the output is going to be interesting. So we're gonna and then forward this stuff into the neural network, right? We're forwarding this, and then we want to print the output. So we're going to print the values that we put in there. Though interestingly, yeah, it will be convenient to actually just do it like that. ZU equal F. So IJ, and how can we get the output? We can do output of the neural network matrix at 0, 0. Right, because the output is a matrix, so, and it has only one number, so that's how we can do that. This is really nice, right? So this macros kind of create this sort of like a syntax, domain-specific language, I would even say. It's almost as easy as, but yeah, but though I never actually used any Python frameworks, do they work like this? Is that how you use them? Right, because I don't really want to touch any of the Python frameworks unless I can implement this shit from scratch myself, unless I fully understand it. I don't like to use things that I don't understand, right? So until I finished with this thing, I'm not touching anything from like TensorFlow or anything like that, right? I want to understand things first. Right. But you don't do a lot of memory dialog and shit. But why do you need to deallocate any memory in here? Because it's going to be deallocated by operating system anyway. And you know what's funny? The memory is allocated only in these two places. So there is a reason why I said that I want the memory allocation to be concentrated in a very small place. So you allocate as much memory as you need for up front, and then none of that process down below allocates any memory. Like none of the memory management involved in this specific region of code. None of it. Right, literally none of it, and that's the beauty of it. So I can increase the amount of iteration, it's not going to leak anything, right? So okay, that's kind of cool, and it works, right? Look at that. So it does act like Zor. That's cool. So now let me remove all of the Zor related stuff, which is not needed because we abstracted all of that away. None of that matters anymore was just like an intermediate thing that we don't need. So the whole thing is, here's the training data, right? We're slicing the training data into these two like input and output matrices, right? So then we define the architecture of the neural network, 2 inputs, 2 inner things, 1 output, right? And we just allocate all of that here. And then we just like training that with a very dumb approach of finite differences and whatnot, but it still drives the cost function down, which is what we want anyway, so who cares, right? So sometimes it doesn't really work the way I want, right? It gets stuck in a really weird place, but anyway, right. So, and why I want you to do all of that, right? Because now I can quite easily change the architecture of the entire neural network. So, for instance, if I want to go back to a single neuron, which cannot represent Zor, I can just remove this entire thing and there you go. So I don't have to rewrite the entire code or anything like that. I just like remove the entire layer. Right. So if you were to use this kind of approach where you would explicitly put all of the arguments, like adding or removing the layer would be a huge pain in the ass. Now here I can just remove one thing. That's it. So, and it's just like, it's a different neural network. Differently connected and stuff like that, right? So the whole neural network is described like with this single line, and I can modify all of that, and I can, for example, confirm that it cannot really, yeah. So I'm trying to, you know, do Zor, and it gets stuck on 0.25. And all of the activations here are the same because Zor is not representable like with this amount of neurons. Like you just can't do that. Though you can do something cool, right? So okay, here's, let's say this is TD Zor. Let's introduce another one here, right? So let's say this is going to be TD OR, right? How about that? TD OR, right? And essentially, this is going to be 0, 0, 0, right? So 1, 1, 1, there we go. I wonder if I can. Okay, so this one is a bit painful, I think. Damn. So we know that the stride is 3. We can. Okay, so n is the amount of samples, right? Is the amount of rows. Maybe I can just hard code that because I know that it's equal to 4 anyway, so who cares, right? It's always 4 rows, and it's sort of going to be like a standard in here. So that then I can do float TD, right? So, and then just swap between these things like so quite easily, right? So let's take a look at OR, doesn't work. And now I'm going to switch to OR, and OR with a single thing is representable. So it goes towards OR, right? But it can't do Zor. Right, it can't do Zor. But as soon as you add another layer in here, right, we just added another layer in here, it works. Do we have a bias sigmoid? Yes, we do. So let me demonstrate. So, and then forward, there we go. Here's the bias. And here's a sigmoid. So this is the forwarding. It's pretty straightforward. And now we can. We don't have a ReLU yet, but we're gonna add it a little bit later. So what if we actually say, okay, what if we're gonna have 4 of these, 4 of the inner like layers? Is it gonna change anything? Probably not. Yeah, it doesn't really change anything, but it still works. Right, it was just like it's bigger. We can also, at the end of training, we can maybe print the entire neural network that we managed to train. Yeah, so that's the entire neural network. Yeah. So, but this is with 4 hidden things, right? With 4 hidden things, which is completely redundant. I don't think it's needed, but that's the things in here. Does adding more neurons increase learning time? Yeah, I'm pretty sure, because that will basically means that you need to spend more time computing the cost function, because we're using finite differences. And if we were not using finite differences, we were using backpropagation, it's still more parameters to iterate through anyway. It's just like purely based on the amount of iterations you have to make. So it's still going to be slower. Right, so you want to, like, I guess, find the size of the neural network that kind of fits your purpose. So yes. So now we can do more interesting cool shit. For instance, one of the things I want you to do is to have a training data, right, that looks like, I don't know, some, right? And essentially I could say, okay, so here I have like 2 bits, right? So this is an input, and then 2 bits as an output. And then if I put 1 in here, I would expect this thing to be this. If I put 1 to here, I expect this thing to be this, right? And if I do it like that, I expect this thing to be this. Do you guys know what it is? Right, do you guys know what it is? It's a sum, right? So it would be kind of cool to train a neural network that acts like a sum circuit, right, of like a fixed amount of bits, right? It would be kind of interesting, I think. And if we take if we Google up the circuit adder, I have a feeling, I have a strange feeling that circuit adder may require the depth of the neural network equal to the amount of bits it's working with. So for each bit, it may require an additional layer of neural network. Who knows why? Who knows why? Like a full error. I have a feeling, it's my hypothesis, I don't know for sure. I don't know for sure. Because you chain them together. Because we chain them together. Like the output, it goes into the input in another one, and so on and so forth. And I feel like each individual bit may require like literally additional layer, but I don't know that yet. And I want to explore that. Because I already kind of off screen, right, tried to train it, and with just few layers, or just with one hidden layer, it was not really training well. So my hypothesis is that you need a lot of layers here. That's why humans are bad at math. Too many neurons need. Yeah, exactly. But I want to do that already next time, because I'm already streaming for 3 hours. Right, so we're gonna leave that for the next time. So what we managed to do in here, we managed to basically take everything we learned in the previous stream and turn this into a separate framework, which I would like to maybe put onto GitHub, but I'm gonna do that after the stream, right? Because I'm already a little bit tired, so I'm gonna just finish the stream and take a break, and then I'm gonna put it on GitHub. So let me take a look. Did we have any additional subs? I didn't think so. Nobody subs or subscribed. At least Twitch doesn't show me. Right. So I'm just refreshing super quick. Yeah. All right. That's it for today. Thanks everyone who's watching me right now. I really appreciate that. Hope it was interesting. Right. And I see you all next time. So yeah, love you. Mwah.